What invisible force holds entire galaxies in its grip, across millions of light years? If space is mostly empty, why do galaxies still pull on each other? Are they drifting aimlessly or dancing to the rhythm of a cosmic force we barely understand? This isn't just about stars and gas. It's about the space in between. A place so vast, so silent, and yet so powerful. Today we're diving deep into the unseen threads that bind the universe together. This is the gravity between galaxies. When we turn our attention to the vast spaces between galaxies, gravity reveals itself as the universe's chief architect. Despite being the weakest of the fundamental forces, gravity dominates at these scales because of its infinite range and cumulative effect. While electromagnetic forces are typically screened due to the presence of both positive and negative charges, gravity knows only attraction. Each bit of mass adds to the total gravitational influence, creating effects that extend across billions of light years. The gravity between galaxies is exceptionally weak by everyday standards. If you could somehow isolate two galaxies in otherwise empty space, their initial gravitational acceleration toward each other would be imperceptible by human measures. Yet over cosmic timescales, this gentle attraction adds up, drawing galaxies together into clusters, filaments, and the vast structures that form the cosmic web. Between our Milky Way and the neighboring Andromeda galaxy, gravity creates a bond that transcends the 3 million light-years separating them. This gravitational relationship has determined their future, setting them on a collision course that will fundamentally alter both galaxies over the next few billion years. What makes gravity unique is not just its universal presence, but its patience. Electromagnetic forces work effectively, instantaneously, on human timescales. The strong nuclear force operates only over subatomic distances, but gravity works gradually, persistently, across billions of years, slowly but inexorably shaping the largest structures in the universe. As we contemplate gravity's role, it's worth noting that despite our advanced understanding, fundamental questions remain. Why is gravity so much weaker than the other forces? Does it truly operate the same way at all scales? Or might there be subtle variations at cosmic distances? Could alternative theories like modified Newtonian dynamics account for some observations currently attributed to dark matter? These questions remind us that for all our knowledge, gravity retains its mysteries. We have moved from seeing it as a tendency of objects to seek their natural place, to a force acting across empty space, to a curvature in the fabric of reality itself. Each step has brought deeper understanding, yet the journey continues. As we drift through the cosmos tonight, remember that gravity touches everything. It is the silent architect of stars and galaxies, the gentle force that has shaped our universe from its earliest moments to the present day. And in the vast spaces between galaxies, gravity weaves connections that transcend the emptiness, binding the cosmos into a single, integrated whole. Gravity does not push or pull, it bends, and space itself responds. This simple statement contains a profound truth about the nature of our universe. As we journey deeper into gravity's domain, we will see how this bending of space creates the cosmic structures that surround us, from the delicate spiral of a single galaxy to the vast filaments of the cosmic web. Between galaxies, in the seemingly empty void, gravity whispers its influence across millions of light years. In that whisper lies the future shape of our universe. The Sun occupies a relatively orderly region, orbiting about 27,000 light-years from the galactic center at a speed of about 220 kilometers per second. Our orbit is not perfectly circular but slightly elliptical, causing the Sun to move slightly closer to and then farther from the galactic center over millions of years. Our orbit also includes small up and down oscillations through the galactic plane, with a period of about 60 million years. This relative stability has important implications for life on Earth. Regions closer to the galactic center contain more stars, higher radiation levels, and more frequent supernova explosions, potentially threatening to life. Regions in spiral arms experience periodic waves of star formation, also increasing radiation and supernova rates. Our location in a relatively quiet neighborhood between spiral arms may have provided the long-term stability needed for complex life to evolve. The gravitational influence of our galaxy extends far beyond its visible disk. The Milky Way's dark matter halo reaches at least 10 times farther than the stellar disk, encompassing a region more than 1 million light-years in diameter. Within this extended halo orbit dozens of satellite galaxies, small collections of stars bound by the Milky Way's gravitational field. The closest of these satellites, the Large and Small Magellanic Clouds, are visible to the naked eye from the southern hemisphere. These satellite galaxies orbit the Milky Way much as moons orbit planets, their paths determined by our galaxy's gravitational pull. Over billions of years, tidal forces gradually strip stars and gas from these smaller galaxies, creating streams of material that eventually become incorporated into the Milky Way. This process of gravitational cannibalism plays an important role in galactic evolution. The Milky Way has likely consumed hundreds of smaller galaxies throughout its history, their stars now indistinguishably mixed with our galaxy's native population. Evidence of this process appears in the stellar streams discovered in our galaxy's halo, ribbons of stars that share similar orbits and compositions, the remnants of disrupted dwarf galaxies. At the very center of this gravitational complexity lies Sagittarius A star, our galaxy's supermassive black hole. Despite containing the mass of millions of suns, this black hole occupies a region smaller than our solar system. Its gravitational field is so intense that it warps space-time completely back on itself, forming an event horizon beyond which nothing can escape. Stars orbiting close to Sagittarius A star move at tremendous speeds, with the closest known star, S2, reaching velocities of over 7,000 kilometers per second at its closest approach. The orbits of these central stars provided some of the strongest evidence for the existence of the central black hole, their rapid motion indicating the presence of an enormous but invisible mass. While the black hole itself cannot be seen directly, astronomers have observed flares of radiation from gas and dust falling into it. As this material spirals inward, it heats to millions of degrees, emitting X-rays and other forms of high-energy radiation, before disappearing beyond the event horizon. Most large galaxies harbor similar central black holes, some even more massive than our own. In active galactic nuclei, material falling into the central black hole creates brilliantly luminous regions that can outshine all the stars in the galaxy combined. Though our galaxy's central black hole is currently relatively quiet, evidence suggests it may have been more active in the past. The gravitational interactions within galaxies create a dynamic environment that evolves over cosmic time. New stars form from collapsing gas clouds, adding to the galaxy's mass. Supernova explosions and stellar winds eject material back into interstellar space. Density waves move through the galactic disk, triggering bursts of star formation. And beneath it all, the dark matter halo provides the gravitational scaffold that makes these structures possible. Inside every galaxy, gravity whispers in circles. It orchestrates the orbital dance of billions of stars, each following its own path, while contributing to the collective gravitational field. It shapes spiral arms and central bulges, star clusters, and gas clouds. It binds satellite galaxies, and ultimately delivers their material to the larger host. This gravitational whisper creates the galaxies we see, the islands of stars that populate the cosmos. But between these islands, across the seemingly empty void, gravity speaks in a different voice. There, it reaches across millions of light-years, drawing galaxy toward galaxy in a slower, grander dance. Between galaxies, gravity roars. Supercluster, itself just one region of the cosmic web. We occupy neither a major node nor the emptiness of a great void, but a somewhat ordinary location within the web's overall pattern. This positioning reflects the Copernican principle that has guided astronomy for centuries. We occupy no special or central place in the cosmic order. Yet our ability to perceive and comprehend the cosmic web represents something special indeed. Through the unlikely development of intelligence and science on our small planet, the universe has generated observers capable of mapping and understanding its largest structures. In a sense, the cosmic web has become conscious of itself through the minds of astronomers studying its properties. This self-awareness, however limited and imperfect, adds a dimension to the web's existence beyond its physical reality. The cosmic web reminds us that emptiness and connection coexist at the grandest scales. The vast voids that comprise most of the universe's volume exist alongside the intricate filamentary connections between galaxies. Neither component exists without the other. The filaments define the voids, while the voids shape the filaments. This complementary relationship between emptiness and connection echoes philosophical traditions that have long recognized the interdependence of space and substance. As our journey continues, remember that the cosmic web represents gravity's patient work over billions of years. From nearly uniform beginnings, gravity has gradually woven the rich tapestry of filaments and voids that we observe today. Each galaxy, including our own Milky Way, finds its place within this larger structure, its formation and evolution shaped by its location within the web. The cosmos is not random. It is woven, with threads we cannot touch, but we can trace. These words capture the essence of the cosmic web, a structure invisible to our eyes, yet revealed through the patient accumulation of astronomical data. Through gravity's subtle influence, the universe has organized itself into the most extensive pattern we know, a web that spans billions of light years yet follows mathematical principles we can understand. As we drift through this cosmic tapestry in our mind's eye, we see not chaos, but connection, not randomness, but relationship. We witness gravity's grandest creation, the framework that holds the visible universe together across distances so vast that light itself takes billions of years to cross them. And in that pattern, we find both wonder at the universe's complexity and satisfaction in our growing ability to comprehend it. Similarly, voids offer a promising avenue for testing modified theories of gravity. Some alternatives to general relativity predict different behavior in low-density environments than in high-density ones, differences that would be most noticeable in cosmic voids. By comparing the observed properties of voids with predictions from various gravitational theories, researchers can constrain or potentially rule out some modified gravity models. Beyond their scientific value, voids inspire philosophical reflection on the nature of emptiness and its relationship to structure. In many Eastern philosophical traditions, emptiness is not mere absence, but a positive quality, the space that allows form to exist and define itself. Cosmic voids embody this conception, their apparent emptiness playing an essential role in defining the universe's structure. These vast bubbles of relative nothingness remind us that the universe is not uniformly filled with matter, but contains enormous regions where matter is scarce. Yet even in these emptiest reaches, gravity's influence remains, shaping their boundaries and guiding the motions of the few galaxies within them. Emptiness, in the cosmic sense, does not mean the absence of physical law, but a different manifestation of the same principles that operate everywhere. The expansion of space itself appears most clearly in voids, where the opposing pull of matter is weakest. As the universe expands, voids grow faster than average, while dense regions expand more slowly due to their increased gravitational self-attraction. This differential expansion enhances the contrast between voids and filaments over time, making the cosmic web increasingly distinct as the universe ages. In the distant future, as cosmic expansion accelerates under dark energy's influence, voids will come to dominate the universe even more completely than they do today. Matter will increasingly concentrate in isolated, gravitationally bound systems separated by ever-growing voids. Eventually, galaxies beyond our local group will recede so rapidly that they become unreachable even in principle, their light too redshifted to detect. The observable universe will gradually empty as more objects cross this cosmic horizon, leaving our local region increasingly isolated in an effectively empty cosmos. This future emptiness represents the ultimate expression of gravity's relationship with cosmic structure. While gravity works to concentrate matter locally, the accelerating expansion of space, driven by dark energy, works in opposition at the largest scales. The balance between these influences determines the fate of cosmic structure, with current evidence suggesting that expansion will ultimately prevail, creating a universe dominated by emptiness with isolated islands of gravitationally bound matter. Yet even in this distant future of cosmic emptiness, gravity will continue its work within those bound regions, gradually rearranging matter into ever more compact configurations. Stars will burn out, galaxies will merge, and matter will increasingly concentrate around central black holes. The contrast between the emptiness of intergalactic space and the dense concentrations of matter within gravitationally bound regions will become increasingly pronounced. This long-term evolution reminds us that the relationship between gravity and emptiness continues across all of cosmic history, from the nearly uniform early universe through the complex cosmic web of today to the isolated island universes of the distant future. At each stage, emptiness and structure define each other, with gravity determining the boundary between them. As we drift through a cosmic void in our mind's eye, we experience space at its most pristine, regions where matter is sparse and separated by tens of millions of light years. Here, the expansion of the universe proceeds most purely, uncomplicated by the opposing pull of dense matter concentrations. The few galaxies we encounter appear isolated, their evolution determined more by internal processes than by interactions with neighbors. Yet even in this apparent emptiness, we remain within gravity's domain. Each sparse galaxy responds to the gravitational influence of distant matter concentrations, its motion revealing the invisible pull of filaments and clusters that may lie hundreds of millions of light years away. The void itself, defined by its boundary with surrounding structures, represents not the absence of gravity, but a particular configuration of gravitational influence, a region where the gravitational pull points predominantly outward toward the surrounding cosmic web. Emptiness is not the absence of gravity, it is gravity's gentle outline. This simple statement captures the profound relationship between cosmic voids and the gravitational processes that shape the universe. What appears as emptiness actually reveals gravity's work in complementary form, showing where matter has been drawn away rather than where it has accumulated. The void boundaries trace the gravitational watershed, the dividing line between regions that feed different filaments and clusters. In this sense, voids represent not gravity's failure but its success, regions where gravity has effectively cleared matter from vast volumes of space and directed it toward growing structures elsewhere. They remind us that cosmic evolution involves not just building up, but also clearing away. Not just concentration, but also evacuation. Both processes reflect gravity's persistent influence across cosmic time and space. As our journey through gravity's domain continues, we carry with us this deeper understanding of emptiness and its relationship to structure. The cosmic voids, far from being irrelevant gaps between interesting regions, emerge as essential components of an interconnected whole, their properties and evolution revealing fundamental aspects of how gravity shapes the universe across its largest scales and longest timescales. As we near the end of this chapter, consider once more the patient contest between gravity and expansion that has shaped our universe from its earliest moments and will determine its ultimate fate. For billions of years, these influences have maintained a dynamic balance, allowing matter to coalesce into complex structures while preventing a complete gravitational collapse. This balance has created the conditions for stars, planets, and life to exist, at least on our small world, orbiting an ordinary star in an average galaxy. The discovery of cosmic acceleration suggests that this balance will eventually shift, with expansion gradually overcoming gravity at the largest scales. But gravity will not disappear. It will continue its work within gravitationally bound systems, maintaining structure against the background of accelerating expansion. Galaxies and clusters will remain intact even as they separate from each other across ever-growing voids. In this sense, both gravity and expansion achieve a kind of victory, each dominating different scales in the cosmos. Expansion, driven by dark energy, shapes the largest scales, determining how structures relate to each other across cosmic distances. Gravity maintains its influence within those structures, continuing to shape their internal evolution over timescales that stretch into the unimaginable future. In the long silence ahead, gravity will be the last voice. When stars have burned out, when galaxies have merged or dispersed, when ordinary matter has decayed or collapsed into black holes, gravity will continue its patient work, drawing whatever remains into ever more stable configurations against the background of an ever-expanding void. It will remain the universe's most patient sculptor, shaping whatever structure can exist in a cosmos growing increasingly cold and empty. This persistence speaks to gravity's fundamental nature as the curvature of space-time itself, an integral aspect of the universe's structure, rather than a force imposed upon it. As long as matter exists, gravity will shape its distribution. And in that shaping lies the universe's ongoing story, a narrative written in the language of attraction across distances, a saga that began in the Big Bang and stretches toward a future so distant that our current age appears as merely the opening moment of a story still unfolding. Across the silent sea of space, galaxies move not alone, but together, their paths shaped not by light, but by something deeper, something quieter, something constant. This is the story of the gravity between galaxies, the threads that hold the universe in place. In the vast darkness between stars, a gentle force works without rest. It does not flash like starlight or roar like stellar winds. Instead, it whispers across billions of years, drawing matter toward matter in an endless cosmic dance. When you look up at the night sky, you see points of light, stars, distant suns, perhaps a planet or two. What you cannot see is the invisible architecture that arranges them all, the ceaseless pull that shapes our universe. Gravity. We know it as the force that keeps our feet on the ground, that pulls a dropped object toward Earth. But this everyday experience is merely the smallest expression of a force that spans the cosmos. Between galaxies, gravity stretches across millions, even billions of light years. It creates bridges of influence where nothing visible exists. It orchestrates the motions of trillions of stars, gathering them into clusters, superclusters, and the vast filaments of the cosmic web. Tonight, we drift through the universe to witness gravity's quiet power, not as equations or abstractions, but as the fundamental storyteller of cosmic history. From the smallest asteroid to the largest supercluster, gravity connects everything to everything else. Close your eyes. Imagine yourself floating in the space between galaxies. Feel the gentle tug from every direction. That sensation, that pull toward everything else that exists, that is gravity's embrace. And in that embrace, the entire universe finds its shape. The story of gravity is the story of patience. While light races across the cosmos in an instant, gravity works across eons. It does not demand attention. It simply waits, pulls, shapes. The galaxies we see tonight have been arranged by gravitational forces that began their work billions of years ago, when the universe was young. In our human experience, gravity seems immediate. Drop an apple, and it falls without delay. But on the cosmic scale, gravity's work unfolds like a slow symphony, each movement spanning millions of years, spiral around galactic centers. Galaxies themselves drift toward one another across the void. Clusters of galaxies merge into superclusters, drawn together by invisible connection. What makes gravity unique among the fundamental forces is its unrelenting nature. It never stops, never weakens beyond recovery, never turns off. Across any distance, no matter how vast, gravity maintains its gentle hold. Between our Milky Way and the most distant galaxy we can observe, there exists a gravitational relationship, impossibly faint, yet mathematically certain. This connection creates a universe that breathes together, that moves as one vast system. Nothing exists in true isolation. Even in the emptiest void between galactic clusters, the fabric of space-time itself carries gravitational waves, ripples in the cosmic ocean that spread the influence of distant events. As we begin our journey tonight, let go of the boundaries that separate one object from another. In the language of gravity, everything is connected. The moon to the Earth to the sun, our solar system to the Milky Way, and our galaxy to every other island of stars that populates the universe. We will travel from the familiar to the incomprehensible, from the gravity we feel to the gravity we can only imagine. We will see how this one force shapes everything from the orbit of planets to the grandest structures in the cosmos, how it creates order from chaos, pattern from randomness, and perhaps most wonderfully, how gravity itself tells us about matter we cannot see. For in its pull lies the evidence of dark matter, the mysterious substance that outweighs all visible stars and galaxies. Through gravity's lens, we glimpse the invisible scaffolding of creation. So settle in, breathe deeply, and let us follow gravity's path together, from the smallest whisper to the grandest cosmic roar. For in understanding this silent force, we understand the very architecture of existence. In the beginning, there was light, and there was gravity. Light we could see, streaming across the newborn universe. Gravity we could only infer, shaping that same universe from its first moments. Both fundamental, both essential, but working on vastly different timescales. Listen to the silence between my words. That pause, that space, that is where gravity lives. Not in the sound, but in the waiting between. Not in the event, but in the inevitable pull that follows. Gravity speaks in the language of curves. It does not travel in straight lines, but follows the contours of space itself. Einstein showed us that what we experience as a force is actually the bending of space-time. Mass tells space how to curve, and curved space tells matter how to move. When you gaze at a distant galaxy through a telescope, you are looking back in time. The light from that galaxy has traveled for millions, perhaps billions of years to reach your eye. But during all that time, the gravity of that same galaxy has been reaching out to us as well, tugging gently at our own Milky Way, influencing our cosmic neighborhood in ways too subtle to notice in a human lifetime. The poet John Donne wrote that no man is an island. In the cosmic sense, no galaxy is an island either. Each is connected to all others through gravity's web. The Andromeda Galaxy, our nearest large galactic neighbor, is falling toward the Milky Way at more than 100,000 kilometers per hour. Not for millions of years will they meet, but gravity has already determined their fate, has already begun the merger that will transform them both. Tonight, as you drift towards sleep, consider that you are experiencing gravity in its most familiar form. Your body rests against the bed, held by the same force that keeps planets in orbit and guides the motion of galaxy clusters. The same physics applies at all scales, an elegant consistency that unites the cosmos. And while you sleep, galaxies will continue their slow dance across the void, moving not randomly, but according to gravity's gentle guidance. Stars will continue to orbit galactic centers. Planets will trace their elliptical paths around stars. Moons will circle planets, all in a nested harmony of gravitational relationships. The universe breathes through gravity. It is its pulse, its rhythm, its most fundamental organizing principle. Without it, the cosmos would be formless, a chaos of particles rushing apart with no structure, no galaxies, no stars, no planets, no possibility of life. With this introduction, we begin our journey through gravity's domain, from its everyday effects to its cosmic implications, from the fall of an apple to the collision of galaxy clusters, from what we can observe to what we can only deduce. The gravity between galaxies awaits us. Let us follow where it leads. Gravity does not push or pull, it bends, and space itself responds. Perhaps no force is more familiar to us than gravity. From our first moments, we learn its constant presence, the steady weight of our bodies against the earth, the predictable fall of objects released from our hands, the reliable rhythm of the tides, pulled by the moon's gravitational embrace. Yet for all its familiarity, gravity remains profoundly mysterious. Its true nature has challenged our greatest minds and continues to puzzle scientists today. To understand the gravity between galaxies, we must first understand gravity itself, not just as we experience it in our daily lives, but as it truly operates across the cosmos. For thousands of years, gravity seemed simple enough. Objects fall because it is their nature to seek the center of the Earth. The ancient Greeks believed that each element had its natural place. Earth at the center, then water, then air, then fire reaching toward the heavens. Objects fell because they were returning to where they belonged. This view persisted until the scientific revolution, when minds like Galileo Galilei began to question the ancient wisdom. By dropping objects from the Leaning Tower of Pisa, Galileo discovered something remarkable. Contrary to Aristotle's teaching, heavy objects do not fall faster than light ones. In the absence of air resistance, a feather and a cannonball would reach the ground at the same moment. But it was Isaac Newton who gave us the first mathematical description of gravity. Legend tells us that the fall of an apple in his garden inspired Newton to realize that the same force that pulls an apple to the ground also keeps the moon in orbit around the Earth. This insight led to his universal law of gravitation. Published in 1687, Newton described gravity as a force acting between any two objects with mass. The strength of this force depends on two factors. First, the masses of the objects, with greater mass creating stronger gravity. Second, the distance between them, with the force weakening by the square of that distance. This inverse square relationship is crucial. Double the distance and gravity becomes 4 times weaker. Triple the distance and it becomes 9 times weaker. This explains why we feel Earth's gravity strongly, but barely notice the gravitational pull of the distant moon, despite its substantial mass. Newton's description of gravity worked remarkably well for predicting the motion of planets and moons. It explained the tides, the orbits of comets, and much more. For over 2 centuries, it seemed complete. But there was a problem. Newton's equations described how gravity worked, but not why. How could objects exert forces on each other across empty space? Newton himself considered this action at a distance troubling, writing that it was inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact. Enter Albert Einstein. In 1915, after years of intensive work, Einstein published his general theory of relativity, forever changing our understanding of gravity. According to Einstein, gravity is not a force at all, at least not in the conventional sense. Instead, it is a consequence of the way mass warps the fabric of space-time. Imagine space-time as a vast rubber sheet. A massive object like the Sun creates a deep depression in this sheet. Smaller objects like planets follow curved paths around this depression, not because they are being pulled, but because they are following the shortest path through curved space. Einstein's vision of gravity is both simpler and more profound than Newton's. Matter tells space-time how to curve, and curved space-time tells matter how to move. No mysterious action at a distance required. Just the elegant geometry of a universe in which space and time are woven together into a single continuum. General relativity made predictions that Newton's theory could not. It explained a peculiar anomaly in Mercury's orbit that had puzzled astronomers for decades. It predicted that light, which has no mass, would nevertheless be bent by gravity because it follows the curves of space-time. This prediction was dramatically confirmed during a solar eclipse in 1919, when stars visible near the edge of the eclipsed sun appeared slightly displaced from their known positions, their light bent by the sun's gravitational field. Einstein's theory revealed that gravity is not instantaneous, as Newton had assumed. Changes in gravitational fields propagate at the speed of light. If the sun were to suddenly disappear, the Earth would continue orbiting the vanished star for about 8 minutes before the gravitational change reached us. The same time it takes sunlight to reach Earth. One of general relativity's most remarkable predictions was the existence of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves, traveling at the speed of light, carry energy across the cosmos, subtly stretching and compressing space itself as they pass. For a century, these waves remained theoretical, too faint to detect. But in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by recording gravitational waves produced by the collision of 2 black holes more than 1 billion light-years away. The signal was incredibly faint, changing the length of LIGO's 4-kilometer-long detectors by less than the width of a proton. Yet it confirmed another aspect of Einstein's revolutionary vision. While Einstein's description of gravity has superseded Newton's, we still use Newton's equations for most practical purposes. They are simpler and provide excellent approximations in weak gravitational fields like Earth's. General relativity becomes essential only in extreme conditions, near black holes or other very massive objects, or when calculating the trajectories of spacecraft with extreme precision. Both Newton and Einstein described how gravity behaves, but neither fully explained why it exists. In modern physics, gravity is understood as one of the four fundamental forces of nature, alongside electromagnetism and the strong and weak nuclear forces. Yet gravity stands apart from the others. It is by far the weakest force, yet dominates at cosmic scales because it always attracts and never repels. Moreover, while the other forces have been united in a quantum framework, gravity has resisted integration into this scheme. Quantum gravity, a theory that would reconcile general relativity with quantum mechanics, remains one of physics' holy grails. String theory, loop quantum gravity, and other approaches offer promising avenues, but definitive evidence remains elusive. What we do know is that gravity works the same way everywhere in the universe. The same equations that describe an apple falling from a tree also describe galaxies attracting one another across millions of light years. The same principles that govern the Moon's orbit around Earth also govern the motion of stars around the center of the Milky Way. This universality is remarkable. In a cosmos of bewildering diversity, gravity provides a consistent framework, a universal language spoken by all matter. Consider how gravity manifests across different scales. At the human scale, it keeps our feet on the ground and gives weight to our bodies. At the planetary scale, it shapes worlds into spheres and holds atmospheres in place. Gas giants like Jupiter are dominated by gravity, their enormous mass compressing their centers to incredible pressures. At stellar scales, gravity becomes even more dramatic. Stars form when gravity overcomes the outward pressure of gas in interstellar clouds, pulling matter together until it becomes dense enough for nuclear fusion to begin. Throughout a star's life, gravity wages a constant battle against the outward pressure of this fusion. When the fuel runs out, gravity wins, compressing dying stars into white dwarfs, neutron stars, or black holes, depending on their mass. Black holes represent gravity in its most extreme form. Here, mass becomes so concentrated that space-time curves completely back on itself, forming an event horizon beyond which nothing, not even light, can escape. At the center may lie a singularity, a point where our current theories break down entirely. Yet even these cosmic extremes follow the same gravitational principles that govern falling apples. The difference is merely quantitative, not qualitative. Gravity scales with mass and distance according to the same mathematical relationships everywhere in the universe. Inside every galaxy, gravity whispers in circles, but between them, it roars. Imagine yourself soaring above the Milky Way, our home galaxy. From this cosmic vantage point, you would see a vast spiral of stars, a glittering pinwheel against the darkness of space. Nearly 200 billion stars, arranged not randomly, but in an elegant, organized pattern. This is gravity's handiwork, its patient sculpting over billions of years. A galaxy is gravity's masterpiece, a delicate balance between the inward pull of countless stars and the outward momentum of their orbital motion. Without gravity, these stars would fly apart, scattering into the void. Instead, they remain bound together, their collective mass creating a gravitational embrace that can span over 100,000 light-years. At the human scale, we experience gravity as a vertical force, always pulling downward toward the center of the Earth. But within a galaxy, gravity creates a different kind of motion. Here, stars do not fall inward, but orbit around the galactic center, much as planets orbit around the Sun. This orbital dance occurs because each star carries momentum, moving sideways at tremendous speeds even as gravity pulls it toward the center. The result is not a collapse, but a stable orbit. For most stars in the Milky Way's disk, including our Sun, these orbits trace roughly circular paths around the galactic center. Our Sun completes one such orbit approximately every 230 million years. a period astronomers call a cosmic year. Since its birth about 4.5 billion years ago, our Sun has completed only about 20 circuits around the galaxy. This orbital motion follows predictable patterns. In a simplified model where all mass is concentrated at the center, objects closer to the center should orbit faster than those farther away, just as Mercury orbits the Sun faster than Earth, and Earth faster than Mars. This relationship, described by Johannes Kepler for planetary motion and later explained by Newton's laws, would predict that a galaxy's rotation speed would decrease with distance from its center. But when astronomers measured the actual rotation curves of galaxies, beginning with Vera Rubin's pioneering work in the 1970s, they discovered something unexpected. Stars at the edge of galaxies orbit at nearly the same speed as those closer to the center. Rather than falling off with distance, rotation speeds remain relatively flat across most of a galaxy's disk. This contradiction between expectation and observation presented a profound puzzle. Either our understanding of gravity was incomplete, or galaxies contained far more mass than we could see. Most astronomers and cosmologists have concluded the latter, giving rise to the concept of dark matter, an invisible substance that reveals itself only through its gravitational effects. According to this theory, visible stars and gas account for only about 15% of a galaxy's total mass. The remaining 85% consists of dark matter, arranged in a roughly spherical halo that extends far beyond the visible disk. This dark matter halo provides the extra gravitational pull needed to explain the unexpectedly fast rotation of a galaxy's outer regions. While the nature of dark matter remains one of the great mysteries of modern physics, its gravitational effects within galaxies are well documented. Without this invisible component, galaxies as we observe them could not exist. Their stars would either disperse or distribute themselves differently. At the very center of most large galaxies lies another gravitational marvel, a supermassive black hole. In our Milky Way, this central black hole, named Sagittarius A star, contains the mass of approximately 4 million suns, compressed into a region smaller than our solar system. Despite this enormous mass, the central black hole contributes relatively little to the overall gravitational field of the galaxy. Its influence dominates only in the immediate vicinity of the galactic center, affecting the orbits of stars within a few light years. Beyond this central region, the combined gravity of all the galaxy's stars and its dark matter halo determines the orbital patterns. The intricate dance between gravity and orbital motion shapes not just the overall structure of galaxies but their varied forms. Astronomers classify galaxies into several main types, each representing a different gravitational arrangement. Spiral galaxies like our Milky Way have most of their stars arranged in a flattened disk with spiral arms, a central bulge of older stars, and often a bar-like structure through the center. Their distinctive spiral arms are not fixed structures, but density waves, regions where stars and gas temporarily bunch together as they orbit. These density waves trigger star formation, creating the bright blue regions of newly born stars that make spiral arms so prominent. Elliptical galaxies lack the elegant spiral pattern and appear as smooth, featureless ellipsoids. These galaxies contain primarily older stars and little gas for new star formation. Their stars follow more random orbital paths rather than the organized rotation of spiral galaxies. This difference reflects their formation history, with elliptical galaxies often resulting from the collision and merger of smaller galaxies, events that disrupt orderly orbital patterns. Irregular galaxies show no clear structure at all, their stars and gas distributed chaotically. Many irregular galaxies have experienced recent gravitational disturbances, either from internal processes or external interactions with neighboring galaxies. Within each galaxy type, gravity creates various features that contribute to the galaxy's character. In the Milky Way and other spiral galaxies, the central bulge consists of older stars in randomized orbits, similar to a small elliptical galaxy embedded within the spiral. Surrounding this bulge, the thin disk contains younger stars, star-forming regions, and the distinctive spiral arms. Beyond the visible disk lies the stellar halo, a sparse population of ancient stars in elongated orbits that take them far above and below the galactic plane. And extending even further is the dark matter halo, its invisible mass providing most of the galaxy's gravitational influence. The interactions between these components create each galaxy's unique gravitational signature. In some galaxies, the central regions contain enough mass to create a bar-like structure, a concentration of stars in elongated orbits that rotates as a unit. In others, tidal interactions with neighboring galaxies pull streams of stars into extended tails and bridges. These gravitational features evolve over time. Spiral arms come and go, bars may form or dissolve. The overall structure of a galaxy reflects both its formation history and its ongoing gravitational dynamics. Gravity within galaxies operates across multiple scales simultaneously. At the smallest scale, individual stars exert gravitational influence on their planets and on neighboring stars. Star clusters, containing dozens to millions of stars, create local gravitational wells within the larger galactic field. Giant molecular clouds, the birthplaces of new stars, collapse under their own gravity even as they orbit within the galaxy. On larger scales, spiral arms and other density features create gravitational patterns that influence the motion of stars and gas. And at the galactic scale, the combined gravitational field shapes the overall structure and determines the boundary between the galaxy and intergalactic space. Despite this complexity, the same gravitational principles apply throughout. Einstein's curved spacetime describes the path of a planet around a star, just as it describes the orbit of a star around the galactic center. The mathematics may become more complex when dealing with millions or billions of gravitational sources, but the underlying physics remains the same. Within this gravitational ecosystem, stars follow a variety of orbital paths. Most stars in the disk move in nearly circular orbits aligned with the galactic plane. Their orbital speeds typically range from about 100 to 300 kilometers per second, fast enough to cross the distance from Earth to the Moon in less than 20 minutes. Stars in the bulge and halo follow more eccentric orbits, often tilted at steep angles to the galactic plane. These stars may plunge through the disk during part of their orbit, then soar far above or below it before returning. Some halo stars travel in retrograde orbits, moving in the opposite direction to the galaxy's overall rotation. It stretches farther than we see. It waits longer than we live. And still, it pulls. From our vantage point within the Milky Way, galaxies may appear as fixed points of light, unchanging over a human lifetime. This perception is an illusion born of our brief existence. Galaxies are not static objects, but dynamic systems in constant motion. They rotate, they drift, hide, and merge. And all of these movements are orchestrated by gravity, the silent conductor of the cosmic symphony. We have explored how gravity shapes the internal structure of galaxies, binding billions of stars into spirals, ellipsoids, and irregular forms. Now we turn our attention outward to the vast spaces between these island universes, where gravity's influence extends across millions and even billions of light years, drawing galaxies into relationships that will determine their ultimate fate. Unlike stars within a galaxy, which orbit around a common center, galaxies themselves move through space in more complex patterns. They respond not just to their nearest neighbors, but to the combined gravitational pull of all matter in the universe, visible and invisible. This creates a cosmic web of motion, with each galaxy following a path determined by the distribution of mass across cosmic distances. The most dramatic example of intergalactic gravity at work lies close to home. Our Milky Way and the neighboring Andromeda Galaxy, also known as Messier 31, are moving toward each other at approximately 110 kilometers per second. This cosmic collision course is driven by their mutual gravitational attraction, pulling them together across the 3 million light-years that currently separate them. Although this speed may seem modest compared to the orbital velocities of stars within galaxies, over cosmic timescales, it adds up. Approximately 4.5 billion years from now, the Milky Way and Andromeda will begin a gravitational dance that will forever alter both galaxies. Their first approach will trigger gravitational distortions, pulling out long tidal tails of stars and gas. They will swing past each other, then loop back around for subsequent encounters, each passage bringing them closer to a complete merger. Computer simulations suggest that after several billion years of this gravitational ballet, the two spiral galaxies will merge into a single, larger elliptical galaxy, sometimes whimsically called Milkomeda or Andromeda Way, the ordered spiral patterns will dissolve as stars are thrown into more random orbits. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other and merge, releasing enormous gravitational energy in the process. Despite the cosmic scale of this collision, individual stars are unlikely to impact one another. The distances between stars are so vast compared to their size that even when galaxies intersect, their stars simply pass by each other, like ships in the night. However, the gravitational disruption will fundamentally reshape both galaxies, and the compression of gas clouds may trigger bursts of new star formation. Our Sun will likely be thrown into a different orbit during this merger, perhaps ending up far from the center of the new galaxy. If humanity or its descendants still exist, they will witness a dramatically altered night sky, with the familiar band of the Milky Way replaced by a more three-dimensional distribution of stars, stretching in all directions. This future collision between the Milky Way and Andromeda is not an anomaly, but part of a larger gravitational gathering. Both galaxies belong to the Local Group, a collection of more than 50 galaxies bound together by gravity. Most members of the Local Group are dwarf galaxies, much smaller than the Milky Way or Andromeda, and many orbit as satellites around these two giants. The Local Group spans a region about 10 million light-years in diameter, held together by the combined gravitational influence of all its members. This influence creates a boundary beyond which the expansion of the universe overpowers the Local Group's gravitational pull. Within this boundary, galaxies move relative to each other, according to their gravitational attractions. Beyond it, the cosmic expansion dominates, carrying more distant galaxies away from us at ever-increasing speeds. Our Local Group is just one of many such galaxy groups scattered throughout the universe. These groups vary in size from a few galaxies to dozens, each representing a gravitational gathering within the larger cosmic structure. And just as gravity draws individual galaxies into groups, it also organizes these groups into larger clusters. Galaxy clusters represent the next level in the hierarchy of cosmic structure. They contain hundreds to thousands of galaxies, all bound together by gravity into regions typically spanning 15 to 20 million light-years. The combined mass of a galaxy cluster, including the hot gas that fills the space between galaxies and the invisible dark matter that dominates the cluster's gravity, can reach quadrillions of times the mass of our Sun. Within these clusters, galaxies orbit around a common center of mass, much as stars orbit within individual galaxies. However, these orbits are far less ordered than those within spiral galaxies. Cluster galaxies follow more random paths, frequently altering each other's trajectories through gravitational interactions. This dynamism leads to frequent galaxy mergers, particularly in the dense central regions of clusters. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, contains approximately 1,500 galaxies and lies about 54 million light-years from Earth. At its center sits Messier ET7, a giant elliptical galaxy that has likely grown to its enormous size by consuming smaller galaxies over billions of years. Other well-known clusters include the Coma cluster, containing thousands of galaxies about 320 million light-years away, and the Fornax cluster, with about 60 large galaxies, approximately 65 million light-years distant. These clusters exert such strong gravitational influence that they affect the motion of galaxies and groups tens of millions of light-years away. Our Local Group, for instance, feels the gravitational pull of the Virgo cluster, creating what astronomers call the Virgocentric flow, a general movement of nearby galaxies toward this massive concentration of matter. Just as galaxies within clusters interact and sometimes merge, galaxy clusters themselves are drawn together by gravity into even larger structures called superclusters. These superclusters can span hundreds of millions of light-years and contain dozens of individual clusters, plus thousands of galaxy groups and isolated galaxies. Our Local Group resides on the outskirts of the Virgo supercluster, sometimes called the Local Supercluster, a vast collection of galaxy groups and clusters centered on the Virgo cluster. More recently, astronomers have recognized that the Virgo supercluster is itself part of an even larger structure called Laniakea, meaning immense heaven in Hawaiian. This enormous gravitational collection contains about 100,000 galaxies spread across a region roughly 500 million light-years in diameter. These nested layers of structure, from individual galaxies to groups to clusters to superclusters, all arise from the same fundamental process: the gravitational attraction between masses across cosmic distances. Despite the immense voids that separate galaxies, gravity bridges these gaps, creating relationships that shape the evolution of every galaxy in the universe. The movement of galaxies through space creates another fascinating gravitational phenomenon: tidal interactions. Just as the moon's gravity creates tides in Earth's oceans, galaxies can raise tidal forces in one another when they pass close by. These forces stretch and compress the galaxies, sometimes drawing out long streamers of stars and gas called tidal tails. The Antennae galaxies, located about 65 million light-years from Earth, provide a spectacular example of these tidal interactions. This pair of colliding galaxies has developed long, antenna-like tails of stars, stretching far beyond their main bodies. Similarly, the Mice galaxies, named for their long tails resembling mice, show the dramatic effects of gravitational tides. During a close galactic encounter, these tidal interactions do more than just reshape galaxies visually. They can trigger waves of star formation as gas clouds are compressed by the changing gravitational field. They can strip gas from galaxy disks, either pulling it into long filaments or heating it until it escapes into intergalactic space. And they can reshape the orbits of stars, particularly at the galaxy's edges, where the gravitational binding to the home galaxy is weakest. Over time, repeated tidal interactions can completely transform galaxies. Spiral galaxies may lose their delicate disk structures, their stars redistributed into more random, three-dimensional arrangements characteristic of elliptical galaxies. Gas may be stripped away, shutting down star formation and leaving the galaxy to age, as its existing stars gradually die out. Or conversely, gas clouds may be compressed, igniting bursts of star formation that temporarily outshine the rest of the galaxy. The outcome of these gravitational encounters depends on many factors: the relative masses of the interacting galaxies, their relative speeds, the angle of approach, and whether the encounter leads to a complete merger or just a gravitational perturbation as the galaxies pass by each other. Computer simulations allow astronomers to model these complex interactions, predicting how specific galactic encounters will unfold over billions of years. Beyond their effects on individual galaxies, gravitational interactions between galaxies play a crucial role in the overall evolution of the universe. In the early cosmos, most galaxies were smaller, gas-rich, and actively forming stars. Over time, gravity has drawn these smaller building blocks together into the larger galaxies we see today through countless mergers and acquisitions. This hierarchical growth, directed by gravity, helps explain the diversity of galaxies we observe. Galaxies that have experienced many mergers tend to become ellipticals, their orderly rotations disrupted by the gravitational chaos of repeated collisions. Those that have evolved in relative isolation are more likely to maintain their spiral structure, and those currently undergoing significant interactions often appear irregular or distorted, caught in the midst of gravitational transformation. The current understanding of galactic evolution suggests that most large galaxies have grown through mergers rather than forming all at once. Our own Milky Way bears the scars of this process in the form of stellar streams in its halo, the remnants of smaller galaxies, torn apart by its gravitational field. The Sagittarius dwarf spheroidal galaxy, one of the Milky Way's satellite galaxies, is currently being disrupted by these tidal forces, its stars gradually becoming incorporated into our galaxy. Within galaxy clusters, gravitational effects become even more pronounced. The combined gravitational field of the entire cluster creates a deep potential well, making it difficult for galaxies to escape once they fall in. As galaxies orbit within this well, they experience a process called ram pressure stripping. This occurs when a galaxy moves through the hot, diffuse gas that fills the space between cluster galaxies. The pressure of this motion can push gas out of the moving galaxy, much as a strong wind might blow leaves from a tree. Over time, This process removes much of the gas from galaxies in dense cluster environments, effectively shutting down their ability to form new stars. This explains why galaxy clusters typically contain a higher proportion of elliptical and lenticular galaxies, which have little ongoing star formation, compared to the general field where spirals are more common. The gravitational influence of galaxy clusters extends beyond their visible boundaries. Dark matter, which constitutes about 85% of the cluster's mass, forms an extended halo that reaches far beyond the region where galaxies are concentrated. This halo affects the motion of light passing through it, creating a phenomenon called gravitational lensing. When light from distant galaxies passes through a galaxy cluster, the cluster's gravity bends the light path, similar to how a glass lens bends light. This can create multiple images of the same background galaxy, distort galaxy shapes into arcs or rings, and magnify distant objects that would otherwise be too faint to detect. By carefully measuring these lensing effects, astronomers can map the distribution of dark matter within and around galaxy clusters, revealing the invisible gravitational scaffold that shapes the visible universe. The same physics that governs the orbits of binary stars also applies to pairs of galaxies. Many galaxies exist in gravitationally bound pairs, orbiting around their common center of mass. The Large and Small Magellanic Clouds, visible from the southern hemisphere, form such a pair, though both are also orbiting our Milky Way as satellite galaxies. Other galaxy pairs may be more evenly matched in mass, such as the pair of spiral galaxies, Messier 81 and Messier 82, in Ursa Major. These two galaxies, also known as Bode's Galaxy and the Cigar Galaxy, orbit each other while also undergoing tidal interactions that stimulate star formation in both systems. Sometimes, gravitational interactions between galaxies can lead to more exotic outcomes. Ring galaxies, for instance, form when a smaller galaxy passes through the disk of a larger spiral galaxy. The gravitational disruption triggers a circular wave of star formation, propagating outward from the collision point, creating a ring-like appearance. The Cartwheel Galaxy, about 500 million light-years from Earth, exemplifies this rare configuration. Gravity can also create apparent associations between galaxies that are not physically connected. From our perspective, galaxies that lie in the same line of sight may appear close together, even if one is much more distant than the other. Careful measurements of their redshifts, which indicate their relative distances, can distinguish between true gravitational associations and these chance alignments. When we observe distant galaxy clusters, we are seeing them as they were billions of years ago, due to the finite speed of light. This gives us a window into how gravity has shaped cosmic structure over time. In the early universe, galaxy clusters were still forming, with gravity gradually drawing matter together against the overall expansion of space. Today's massive clusters represent the outcome of gravity's patient work over cosmic timescales. The motions of galaxies relative to each other provide crucial information about the amount and distribution of mass in the universe. By measuring how fast galaxies move within clusters, astronomers can calculate the total mass needed to create the observed gravitational effects. Consistently, these calculations indicate far more mass than can be accounted for by visible matter, providing some of the strongest evidence for the existence of dark matter. Similarly, the overall pattern of how galaxies and clusters move through space reveals information about the large-scale structure of the cosmos. Surveys mapping the redshifts of hundreds of thousands of galaxies have revealed a complex network of filaments, walls, and voids, all created by the interplay between gravity and the expansion of the universe. This cosmic web is not static but evolving. Gravity continuously works to enhance its structure, drawing more matter into dense regions and away from voids. If we could somehow watch the universe evolve in fast forward, we would see galaxies flowing along filaments toward cluster intersections, like water moving through a watershed toward lakes. On the very largest scales, gravity competes with the expansion of the universe. While gravity works to pull matter together, cosmic expansion stretches space itself, increasing the distance between unbound objects. The balance between these forces determines the ultimate fate of cosmic structure. Within bound systems like galaxy groups and clusters, gravity has overcome expansion, creating islands of stability in the expanding cosmos. These structures will remain intact even as the universe continues to expand. But beyond a certain distance, expansion dominates, carrying galaxies away from each other at speeds that increase with distance. This expansion does not mean that galaxies are moving through space, but that space itself is stretching between them. Distant galaxies appear to recede from us, not because they are propelled by some force, but because the intervening space is expanding, carrying them along like spots on an inflating balloon. Remarkably, this expansion appears to be accelerating, driven by a mysterious force scientists call dark energy. This acceleration means that galaxies beyond our local group will recede at ever-increasing speeds, eventually becoming unreachable, even in principle, as they cross a cosmic horizon beyond which light from them can never reach us. The interplay between gravity and this accelerating expansion shapes the largest structures in the universe and determines their ultimate fate. Gravity will continue to strengthen the cosmic web locally, while expansion gradually isolates these gravitationally bound regions from each other across ever-growing voids. As we contemplate these vast processes, we are reminded that gravity connects everything across the cosmos. The same force that keeps our feet on the ground also draws distant galaxies together across millions of light years. Despite the apparent emptiness of intergalactic space, invisible gravitational threads connect every mass to every other mass, creating a single, integrated cosmic system. It stretches farther than we see, reaching across distances so vast that light takes billions of years to cross them. It waits longer than we live, operating on timescales that make mountains seem ephemeral. And still, it pulls, drawing galaxy to galaxy in a slow dance that will continue long after our sun has burned out. Gravity's patience is infinite, and in that patience lies the very structure of our universe. Between galaxies, across the void, gravity reaches, and the universe responds. We do not see it, but gravity tells us it is there. Throughout our journey into gravity's domain, we have repeatedly encountered evidence for something unseen, yet profoundly influential. Something that reveals itself not through light, but through its gravitational effects on the visible universe. This invisible presence, which astronomers call dark matter, constitutes approximately 85% of all matter in the cosmos, yet it has never been directly detected. Dark matter stands as one of the most fascinating enigmas in modern science. Unlike the stars, planets, gas, and dust that make up ordinary matter, dark matter neither emits nor absorbs light. It does not interact with the electromagnetic force that governs most physical processes in our daily experience. It passes through normal matter as if neither existed to the other. Yet through gravity, dark matter shapes the largest structures in the universe and determines the fate of galaxies. The story of dark matter begins in the 1930s, when Swiss astronomer Fritz Zwicky was studying the Coma cluster, a dense collection of galaxies about 320 million light-years from Earth. Zwicky measured the velocities of galaxies within the cluster and made a startling discovery. The galaxies were moving so quickly that the cluster should have flown apart long ago, unless it contained far more mass than could be seen in its visible galaxies. To explain this discrepancy, Zwicky proposed the existence of what he called dunkle materie, or dark matter, an invisible substance providing the extra gravitational attraction needed to hold the cluster together. Initially, many astronomers assumed this missing mass might simply be ordinary matter that was too dim to detect, such as brown dwarfs, black holes, or diffuse gas. The mystery deepened in the 1970s, when American astronomer Vera Rubin and her colleague Kent Ford measured the rotation speeds of stars in spiral galaxies. According to the laws of gravity, stars at greater distances from the galactic center should orbit more slowly than those closer in, just as planets farther from the sun move more slowly in their orbits. Instead, Rubin and Ford found that rotation speeds remained roughly constant, with increasing distance from the center, creating what astronomers call flat rotation curves. This unexpected pattern suggested that the mass in galaxies was not concentrated where the visible matter was, but extended far beyond the visible disk in a roughly spherical halo. Subsequent observations confirmed this pattern in galaxy after galaxy, providing compelling evidence that dark matter not only exists, but shapes the structure of galaxy we can observe. Since these pioneering discoveries, evidence for dark matter has accumulated from multiple independent lines of research. When astronomers map the temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, they find patterns that can only be explained if dark matter influenced the distribution of matter in the early universe. Similarly, computer simulations of galaxy formation only produce structures resembling actual galaxies when dark matter is included in the models. Perhaps the most direct evidence comes from gravitational lensing, the bending of light by mass, as predicted by Einstein's general relativity. By carefully measuring how the light from distant galaxies is distorted as it passes near galaxy clusters, astronomers can map the distribution of mass within and around these clusters. These maps reveal substantially more mass than can be accounted for by visible matter, and this extra mass is distributed differently, extending in roughly spherical halos, rather than following the concentrated distribution of visible galaxies. The case of the Bullet Cluster, a collision between two galaxy clusters about 3.7 billion light-years away, provides particularly compelling evidence. As the clusters passed through each other, the visible gas in both clusters collided and slowed down, while the galaxies and dark matter, which do not interact through collisions, continued moving. Gravitational lensing reveals that most of the mass is located where the dark matter should be, not where the visible gas ended up. This spatial separation between visible and invisible mass would be difficult to explain with modified gravity theories that attempt to account for galactic dynamics without dark matter. Whatever dark matter is, it appears to be fundamentally different from the ordinary matter that makes up stars, planets, and living organisms. Ordinary matter consists of atoms built from protons, neutrons, and electrons, particles that interact through the electromagnetic force as well as gravity. Dark matter particles, by contrast, seem to interact only through gravity and possibly the weak nuclear force, passing through ordinary matter with barely any interaction. The leading candidates for dark matter are hypothetical particles that lie beyond the standard model of particle physics. One category, called weakly interacting massive particles or WIMPs, would have masses comparable to atomic nuclei, but interact only through gravity and the weak nuclear force. Another candidate, the axion, would be much lighter, but could exist in sufficient numbers to provide the required mass. More exotic possibilities include primordial black holes formed in the early universe, sterile neutrinos, or even extra-dimensional effects predicted by some versions of string theory. Despite decades of increasingly sophisticated experiments, no definitive detection of dark matter particles has been achieved. Underground detectors shielded from cosmic rays and other background radiation have searched for rare collisions between dark matter particles and ordinary atoms. Particle accelerators have sought to create dark matter particles in high-energy collisions. Astronomers have looked for indirect evidence, such as gamma rays that might be produced when dark matter particles annihilate each other. So far, these efforts have yielded only upper limits on the possible interactions of dark matter, constraining theoretical models but not yet identifying the specific nature of this mysterious substance. While physicists continue the hunt for dark matter particles, astronomers have mapped the distribution of dark matter with increasing precision, revealing its crucial role in shaping cosmic structure. In the early universe, slight variations in the density of dark matter provided the gravitational seeds around which ordinary matter later gathered. Because dark matter interacts only through gravity, its initial density fluctuations were preserved, while fluctuations in ordinary matter were smoothed out by radiation pressure. This allowed dark matter to begin the process of structure formation earlier, establishing the gravitational wells into which ordinary matter later fell. Computer simulations of cosmic evolution show dark matter forming a vast network of filaments, with dense concentrations at intersections. This network, often called the cosmic web, provides the gravitational scaffolding for the visible universe. Galaxies form preferentially along dark matter filaments and cluster at filament intersections, explaining the large-scale distribution of visible matter that we observe. Around individual galaxies, dark matter forms roughly spherical halos that extend far beyond the visible disk. These halos typically contain 5 to 10 times more mass than the visible galaxy, and their gravitational influence determines the orbital speeds of stars and gas at the galaxy's edge. Without these dark matter halos, spiral galaxies as we observe them, could not exist. Their rotation would tear them apart without the additional gravitational binding from dark matter. The distribution of dark matter within galaxies follows a pattern discovered through computer simulations. The density is highest at the center and decreases with distance according to a specific mathematical relationship, though with some variation depending on the galaxy's formation history. This distribution differentiates dark matter from alternative explanations, such as modified gravity theories, which would predict different orbital patterns for stars at various distances from the galactic center. In galaxy clusters, dark matter constitutes an even larger fraction of the total mass, typically about 85%. The remainder consists mostly of hot gas filling the space between galaxies, with the visible galaxies themselves contributing only a few percent of the cluster's total mass. This hot gas, heated to tens of millions of degrees by the cluster's gravitational compression, emits X-rays that astronomers can detect and map. The temperature and distribution of this gas provide another independent measure of the cluster's total gravitational mass, consistently indicating far more matter than is visible. Dark matter's gravitational influence extends beyond individual galaxies and clusters to shape the connections between them. The filaments of the cosmic web consist primarily of dark matter, with visible matter concentrated along their lengths. These dark matter bridges can span tens or hundreds of millions of light years, creating gravitational highways along which galaxies and gas flow toward dense cluster intersections. If we could somehow see dark matter directly, the universe would look radically different. Instead of isolated islands of light separated by vast darkness, we would see a continuous cosmic web of dark matter filaments, with denser concentrations surrounding galaxies and clusters. The visible galaxies would appear as bright decorations along this underlying structure, revealing their true nature as concentrations of ordinary matter that have fallen into pre-existing dark matter gravitational wells. What makes dark matter particularly fascinating is how it reveals the limitations of our perception. For thousands of years, humans assumed that what we could see represented most of what exists. Dark matter humbles this assumption, showing that the majority of matter in the universe lies beyond our direct perception, detectable only through its gravitational effects. Like a cosmic version of Plato's cave, we observe only the shadows of a deeper reality. This limitation extends to life itself. The atoms that make up our bodies and all living things represent a minority component of the universe, different in fundamental ways from the dominant form of matter. Our biology evolved to interact with and perceive ordinary matter through electromagnetic interactions, leaving us blind to the dark matter flowing through our very bodies. Every second, trillions of dark matter particles likely pass through each of us, yet we feel nothing because dark matter interacts only through gravity, and gravity is far too weak at the particle level to detect. Despite this perceptual gulf, dark matter's gravitational influence has been crucial for our existence. Without dark matter, galaxies would not have formed as they did, stars would be distributed differently, and the conditions for life might never have arisen. The invisible scaffolding of dark matter created the conditions for the visible universe we inhabit. The relationship between dark matter and gravity illustrates a profound scientific principle. Forces reveal what our eyes cannot see. Just as magnetic fields revealed the existence of electricity before electrons were detected, and atomic spectra revealed the quantum nature of atoms before subatomic particles were observed, gravitational effects reveal the presence of dark matter before we can directly detect its constituent particles. As our journey through the universe continues, dark matter serves as a humbling reminder that human perception captures only a fraction of reality. Even with our most sophisticated telescopes and instruments, we observe directly only about 15% of the matter in the cosmos. The remaining 85% makes itself known only through gravity's subtle influence on what we can see. Around our own Milky Way, a vast halo of dark matter extends far beyond the visible disk of stars. This halo, containing roughly 1 trillion solar masses of dark matter, dwarfs the roughly 100 billion solar masses of visible stars. The dark matter halo reaches at least 10 times farther than the visible galaxy, encompassing a region more than 1 million light-years in diameter. Within this extended halo orbit, dozens of satellite galaxies, their paths determined primarily by the gravitational field of the dark matter rather than the visible Milky Way. This pattern repeats throughout the universe. Every galaxy we observe is embedded within a larger dark matter halo. These halos interact gravitationally with neighboring halos, drawing galaxies together into groups and clusters. When galaxies collide and merge, their dark matter halos interact and merge as well, though in a manner different from the visible components. While gas clouds collide and stars occasionally pass near each other, dark matter particles simply flow through each other, their paths altered only by the collective gravitational field. Computer simulations of cosmic evolution reveal how dark matter has shaped the universe over time. Starting from the nearly uniform distribution present shortly after the Big Bang, with only slight variations in density from place to place, dark matter gradually clumped together under its own gravity. Small concentrations merged to form larger ones in a hierarchical process that continues today. This bottom-up assembly, with small structures forming first and then merging into larger ones, explains why older galaxies tend to be smaller, while the largest galaxies show signs of multiple mergers. These simulations also predict the existence of many small dark matter halos that contain few or no visible stars. Observations have indeed found numerous dwarf galaxies with unusually high mass-to-light ratios, suggesting they are dark matter, dominated with relatively few visible stars. However, the simulations predict even more of these small halos than we have discovered, a discrepancy known as the missing satellites problem. This could indicate either that many dark matter halos somehow fail to accumulate enough gas to form visible galaxies, or that our simulations need refinement to better match the observed universe. Another challenge for dark matter models is explaining the remarkably tight correlation between the amount of visible matter in galaxies and their gravitational effects. Despite the wide range of dark matter to visible matter ratios across different galaxies, this relationship, known as the radial acceleration relation, is more precise than would naturally be expected if dark matter and visible matter were largely independent components. Some scientists see this as evidence for a deeper connection between dark matter and visible matter, or even as support for alternative theories. While dark matter remains the leading explanation for the gravitational anomalies we observe, some scientists have proposed alternative theories. Modified Newtonian dynamics, or MUND, suggests that gravity behaves differently over very large distances, or at very low accelerations, becoming stronger than Newton's laws would predict. Another approach, called emergent gravity, proposes that what we interpret as dark matter is actually an effect of quantum entanglement between bits of space-time information. However, these alternative theories face significant challenges in explaining the full range of observations, particularly the behavior of colliding galaxy clusters, like the Bullet cluster, and the detailed patterns in the cosmic microwave background. For now, dark matter remains the explanation most consistent with our observations, though its exact nature continues to elude us. The hunt for dark matter particles continues on multiple fronts. Deep underground, detectors filled with tons of liquid xenon or crystals of germanium wait for the rare collision between a dark matter particle and an atomic nucleus. In particle accelerators, physicists search for missing energy that would indicate a dark matter particle escaping the detector. And in space, instruments like the Fermi Gamma Ray Space Telescope look for signals of dark matter particles annihilating each other in dense regions, like the centers of galaxies. Meanwhile, astronomers continue mapping dark matter's distribution with increasing precision. The European Space Agency's Euclid mission, launched to study the effects of dark matter and dark energy on the expansion of the universe, will create the most detailed three-dimensional map of the universe ever made, tracing the influence of dark matter across vast regions of space. Ground-based projects like the Vera-C Rubin Observatory will monitor billions of galaxies, using gravitational lensing to map dark matter across the sky. As we extend our senses through these instruments, we gradually illuminate the invisible architecture that shapes our universe. The dark matter filaments, halos, and clusters revealed by gravity's effects show us a cosmos where the visible is literally outweighed by the invisible, where what we see represents only a fraction of what exists. In this unseen realm, gravity provides our only current window. It serves as the force that connects the visible and invisible components of the universe, allowing us to infer the presence and distribution of matter we cannot directly detect. Through gravity, dark matter speaks to us, revealing its presence through its effects on light and visible matter. We do not see it, but gravity tells us it is there. In this simple statement lies one of the most profound discoveries of modern astronomy, that most of the matter in the universe exists beyond our direct perception, knowable only through its gravitational influence. As we drift between galaxies in our mind's eye, consider that the apparently empty space we traverse is neither empty nor featureless. It contains vast quantities of dark matter, arranged in filaments and halos that guide the motion of every visible object. These invisible threads connect galaxies across millions of light years, drawing them together against the backdrop of an expanding universe. In dark matter's gravitational grip, galaxies find their shape, their motion, and ultimately their destiny. And in studying this unseen component, we glimpse the limits of our perception and the humbling reality that the universe is far richer and more complex than what our eyes can see. The cosmos is not random. It is woven with threads we cannot touch, but we can trace. If we could somehow rise above the universe and view its structure on the largest scales, we would witness a pattern of breathtaking complexity and beauty. Not the random scattering of galaxies through uniform space that early astronomers might have imagined, but an intricate, interconnected network that astronomers call the cosmic web. This vast structure, spanning billions of light years, represents gravity's grandest creation. Like an enormous spiderweb stretched across the cosmos, it consists of dense filaments of galaxies and dark matter that intersect at massive cluster nodes, with vast, nearly empty voids between them. This pattern, invisible to the naked eye yet revealed by our most comprehensive galaxy surveys, tells the story of how gravity has organized matter throughout cosmic history. The cosmic web was not always there. In the universe's earliest moments after the Big Bang, matter was distributed almost uniformly, with only slight variations in density from place to place. These tiny fluctuations, mere ripples in the cosmic density, held the seeds of all future structure. Over time, gravity amplified these initial differences, drawing matter from less dense regions toward more dense ones. What began as subtle variations gradually evolved into the dramatic cosmic architecture we observe today. This transformation occurred primarily through the gravitational influence of dark matter. Because dark matter interacts only through gravity, it began clumping together earlier than ordinary matter, which was still coupled to radiation in the hot early universe. These initial dark matter concentrations created gravitational wells that later attracted ordinary matter, establishing the framework around which galaxies and galaxy clusters would form. Computer simulations allow us to visualize this process, compressing billions of years into minutes. They show how dark matter particles, initially distributed almost evenly, gradually gather into filaments, with denser nodes forming where filaments intersect. Ordinary matter follows, cooling and condensing to form galaxies preferentially along these dark matter filaments, and especially at their intersections. These simulations reveal that the cosmic web is not designed or imposed from outside, but emerges naturally from the interplay between gravity and the universe's expansion. Gravity works to pull matter together, while cosmic expansion stretches space itself, carrying unbound objects away from each other. The competition between these opposing influences creates the characteristic web-like pattern we observe. The largest galaxy surveys have mapped this pattern with increasing clarity. Projects like the Sloan Digital Sky Survey have measured the positions and redshifts of millions of galaxies, allowing astronomers to create three-dimensional maps of the universe, extending billions of light years in all directions. These maps reveal a universe that resembles a cosmic sponge, with galaxy clusters connected by filaments and separated by voids. The filaments of the cosmic web represent the universe's highways, channels along which matter flows toward dense cluster intersections. These filaments can stretch for hundreds of millions of light years, containing thousands of galaxies strung like pearls along their length. While they appear relatively thin in comparison to the voids they separate, these filaments can span millions of light years in width, encompassing numerous galaxy groups and clusters along their extent. Most galaxies reside within these filaments rather than in the voids between them. Our own Milky Way occupies a relatively small filament, sometimes called the local sheet, which itself connects to larger filaments within the Laniakea supercluster. From our position, we can observe portions of several major filaments in different directions, appearing as bands of increased galaxy density across our telescopic surveys. Where filaments intersect, matter accumulates into the densest structures in the universe, galaxy clusters and superclusters. These massive gravitational wells contain thousands of galaxies, vast quantities of hot intergalactic gas, and enormous concentrations of dark matter. The Shapley supercluster, one of the largest structures in our cosmic neighborhood, at a distance of about 650 million light-years, marks a major intersection in the cosmic web, where numerous filaments come together. Between the filaments lie the cosmic voids, enormous bubble-like regions of significantly lower density. These voids typically span tens to hundreds of millions of light-years, with some, like the Buta's void, reaching up to 330 million light-years across. Despite their name, voids are not entirely empty but contain a sparse population of galaxies, typically less than 1/10 the cosmic average density. These void galaxies tend to be smaller, bluer, and more isolated than their counterparts in filaments and clusters. The cosmic web is not static but continues to evolve. Matter flows along filaments toward cluster intersections, gradually depleting the filaments while enhancing the clusters. Voids grow larger as more matter is drawn out of them, and the web as a whole stretches as the universe expands, increasing the distances between unbound structures. This ongoing evolution follows patterns predicted by the laws of gravity. In regions where the density of matter exceeds a certain threshold, gravitational attraction overcomes cosmic expansion, allowing structures to become gravitationally bound. Below this threshold, expansion dominates, and structures continue to move apart. The boundary between these regimes defines the edges of our local group and other galaxy clusters. What makes the cosmic web particularly fascinating is how it bridges the gap between the universe's initial conditions and its current state. The pattern of filaments and voids we observe today was encoded in the minute density variations present just after the Big Bang. These variations, in turn, originated from quantum fluctuations in the even earlier universe, magnified to cosmic scales by a period of accelerated expansion called inflation. Through the cosmic web, we can trace a direct line from the quantum realm to the largest structures in the universe, with gravity serving as the mechanism that translates those initial variations into the complex architecture we observe. This connection underscores the profound unity underlying the apparent diversity of cosmic phenomena. The cosmic web influences not just where galaxies form, but how they evolve. Galaxies in different environments experience different gravitational and hydrodynamic effects, which shape their gas content, star formation rates, and morphologies. Galaxies in dense cluster environments typically contain less gas and form fewer new stars than those in filaments, while galaxies in voids often remain gas-rich with ongoing star formation. These environmental effects arise from both gravitational interactions and gas dynamics. In dense clusters, galaxies frequently pass near each other, experiencing tidal forces that can strip away gas and disrupt orderly rotation. Additionally, the hot intergalactic medium in clusters creates ram pressure as galaxies move through it, pushing gas out of the galaxies like a cosmic headwind. These processes gradually transform spiral galaxies, which actively form stars, into elliptical galaxies with little ongoing star formation. In filaments, gravitational effects are less severe, allowing many galaxies to maintain their spiral structure and gas content. However, the flow of matter along filaments still influences galaxy evolution, directing how gas feeds into galaxies and occasionally bringing galaxies close enough for tidal interactions. The alignment between galaxies and their host filaments, observed in several surveys, suggests that filaments influence even the orientation of galaxy rotation. Void galaxies, by contrast, evolve in relative isolation, rarely experiencing strong gravitational interactions with neighbors. These galaxies tend to be smaller and less massive than average, but often show vigorous star formation due to their relatively undisturbed gas reservoirs. The existence of galaxies in voids presents a mild puzzle for structure formation theories, which must explain how sufficient matter density arose in these underdense regions to form galaxies at all. The cosmic web's influence extends beyond visible galaxies to the distribution of matter in all forms. Intergalactic gas follows the same filamentary pattern, with the densest, hottest gas concentrated in galaxy clusters. This gas, heated to tens of millions of degrees by gravitational compression, emits X-rays that trace the densest regions of the cosmic web. Cooler gas in filaments remains largely invisible to direct observation, but can be detected through its absorption of light from background quasars. Even the vast quantities of dark matter that dominate the cosmic mass distribution follow the web-like pattern, with concentrations in filaments, and especially at their intersections. Gravitational lensing surveys, which map mass by measuring how it bends light from background galaxies, have begun to reveal this dark matter web directly. The Planck satellite's observations of the cosmic microwave background also show the gravitational imprint of the cosmic web, as photons gain or lose energy traversing the web's varying gravitational potential. The cosmic web serves as both stage and actor in the drama of galaxy evolution. It provides the environment in which galaxies form and grow, while simultaneously evolving in response to the flow of matter along its filaments and the expansion of space between them. This reciprocal relationship between galaxies and their large-scale environment makes the cosmic web a key concept in modern cosmology. Our ability to map and understand the cosmic web has grown tremendously in recent decades, thanks to larger galaxy surveys, better computer simulations, and new observational techniques. The Dark Energy Spectroscopic Instrument, for instance, will create a three-dimensional map of the universe using 35 million galaxies and quasars, tracing the cosmic web with unprecedented detail across 11 billion years of cosmic history. New techniques using the hydrogen emission line mapping approach hope to detect the gas in cosmic filaments directly, revealing the distribution of matter between galaxies. These observations allow us to test theories of gravity and structure formation with increasing precision. The exact pattern of the cosmic web, the sizes and emptiness of voids, the thickness and density of filaments, and the clustering of galaxies all depend on the interplay between gravity, cosmic expansion, and the nature of dark matter and dark energy. By comparing observations with simulations based on different cosmological models, astronomers can constrain the fundamental parameters that describe our universe. One particularly interesting aspect of the cosmic web is how similar patterns appear at different scales. The distribution of matter shows fractal-like properties, with filaments, nodes, and voids appearing not just at the largest scales, but also within individual superclusters, and even, to some extent, around individual galaxies. This self-similarity suggests an underlying mathematical order to the growth of cosmic structure, with gravity creating similar patterns regardless of scale. The mathematical tools used to describe the cosmic web draw from diverse fields, including topology, computational geometry, and network theory. Cosmologists use concepts like the genus, which measures the connectivity of a surface, to characterize the complexity of the web's structure. Other approaches identify filaments by tracking the underlying gravitational potential, or by applying machine learning algorithms to recognize patterns in galaxy distributions. These mathematical descriptions reveal the cosmic web as a specific kind of structure, distinct from both random distributions and regular lattices. It represents a natural outcome of gravitational growth from random initial conditions, with a characteristic balance between order and randomness that maximizes complexity. In network terms, the cosmic web combines relatively few steps between any two nodes, with a high degree of clustering, properties that also appear in many biological and social networks. The analogy to a web extends beyond the visual resemblance. Like a spider's web, the cosmic web functions as both structure and trap, providing the framework for galaxy formation while capturing matter flowing along its filaments. Even the voids play an important role, creating the tension that defines the web's geometry, much as the empty spaces in a spider's web are essential to its function. This web-like architecture appears to be a fundamental outcome of gravitational structure formation, not unique to our universe. Computer simulations exploring different cosmological parameters consistently produce similar web-like patterns, though with variations in the relative sizes of filaments and voids. This suggests that any universe governed by gravity would develop a cosmic web, though its specific properties would depend on the starting conditions and the balance between gravitational attraction and cosmic expansion. The tracing of the cosmic web represents one of humanity's most impressive intellectual achievements, allowing us to comprehend structures spanning billions of light-years despite our confinement to a tiny planet orbiting an ordinary star. Through centuries of astronomical observations, mathematical innovations, and technological advances, we have gradually revealed the universe's largest structures so vast that light takes hundreds of millions of years to cross them. This achievement rests on multiple lines of evidence that converge on the same cosmic picture. Galaxy surveys map the visible traces of the web. Gravitational lensing reveals the underlying dark matter distribution. The cosmic microwave background shows the seeds from which the web grew. And computer simulations demonstrate how gravity transforms those seeds into the structures we observe. Together, these approaches provide a consistent and compelling view of the cosmic web's nature and evolution. What makes the cosmic web especially meaningful is how it connects the universe's largest structures to its smallest components. The filaments and voids that span hundreds of millions of light-years arose from quantum fluctuations on subatomic scales, magnified by cosmic inflation and amplified by gravity over billions of years. Through this connection, the cosmic web links the quantum realm to the largest scales we can observe, unifying our understanding across an enormous range of sizes. The web also connects different epochs of cosmic history. The pattern we observe today was encoded in the minute density variations present in the early universe, which in turn reflect even earlier quantum processes. By mapping the cosmic web, we gain insight not just into the current state of the universe, but into its initial conditions and evolutionary path. The web serves as a fossil record of cosmic growth, preserving the imprint of processes that occurred billions of years ago. For all our progress in mapping the cosmic web, much remains unknown. The filaments that connect galaxy clusters likely contain a significant fraction of the universe's ordinary matter in the form of diffuse, hot gas, most of which remains undetected by current instruments. This missing baryon problem suggests that we have directly observed only a small portion of the cosmic web's full structure. Future X-ray and radio observations may reveal this hidden component, completing our picture of the web. Similarly, while we have mapped portions of the cosmic web in our local universe with considerable detail, our knowledge of how the web evolved over cosmic time remains limited. Observations of distant galaxies and quasars provide glimpses of the web at earlier epochs, but constructing a comprehensive picture of its development requires both deeper observations and more sophisticated analysis techniques. Upcoming instruments like the James Webb Space Telescope and the Vera C. Rubin Observatory will help fill these gaps in our understanding. The cosmic web also challenges our spatial intuition. The three-dimensional structure of interconnected filaments and voids defies simple visualization, especially when we consider its evolution over time. Mathematicians and computer scientists continue developing better ways to represent and analyze this complex structure. From novel coordinate systems to multidimensional data visualization techniques, these approaches help translate the abstract mathematics of cosmology into forms that human minds can comprehend. As we contemplate this vast cosmic structure, we might wonder about our place within it. Our Milky Way resides in a relatively small filament within the much larger Laniakea. From the smallest motion to the largest wall, gravity is the same everywhere. As we continue our journey through the gravity-sculpted universe, we ascend to even grander scales. Beyond individual galaxies, beyond galaxy clusters, lie the true titans of cosmic structure: superclusters and walls. These enormous aggregations of matter span hundreds of millions of light-years, representing the largest coherent structures in our universe. They stand as monuments to gravity's patient work across cosmic time, drawing matter together into patterns of breathtaking scale and complexity. Superclusters are exactly what their name suggests: clusters of galaxy clusters. They represent the next level in the hierarchical organization of the universe, with dozens or even hundreds of galaxy clusters and groups bound into loosely connected systems spanning vast regions of space. These structures contain tens of thousands of galaxies, uncountable stars, and enormous quantities of dark matter and intergalactic gas. Unlike individual galaxy clusters, which are gravitationally bound and relatively compact, superclusters are more diffuse structures, extending across much larger volumes of space. They typically span 50 to 150 million light-years, with some stretching even further. At these scales, the universe's expansion becomes significant, creating a tension between gravitational attraction and cosmic expansion that shapes the supercluster's evolution. Our cosmic neighborhood belongs to one such massive structure. For decades, astronomers referred to the Virgo supercluster as our home supercluster, a collection of galaxy groups and clusters centered around the Virgo cluster, about 50 million light-years away. However, more comprehensive mapping revealed that the Virgo supercluster is itself just part of a much larger structure called Laniakea, meaning immense heaven in Hawaiian. Discovered through careful analysis of galaxy motions, Laniakea spans about 500 million light-years and contains approximately 100,000 galaxies, including our Milky Way. What defines Laniakea is not just the physical proximity of its galaxies, but their shared motion. Galaxies within Laniakea are flowing together through space, drawn by gravity toward a dense region called the Great Attractor. This flow pattern reveals Laniakea's true nature as a gravitational watershed. Like raindrops flowing down mountains into a valley, galaxies within Laniakea move along gravitational pathways toward common destinations. These pathways follow the dark matter distribution, which provides most of the gravitational attraction, but remains invisible to direct observation. Beyond Laniakea lie other superclusters, separated by vast cosmic voids. The Shapley supercluster, about 650 million light-years away, is one of the most massive known concentrations of galaxies, containing dozens of rich galaxy clusters and exerting a measurable gravitational pull on our local group. The Perseus-Pisces supercluster stretches across more than 300 million light-years, forming an arc of galaxies visible in our sky. The Coma supercluster, Hercules supercluster, and many others populate our wider cosmic neighborhood, each representing an enormous concentration of matter bound together by gravity's subtle influence. What makes superclusters particularly interesting is their transient nature. Unlike individual galaxies or even galaxy clusters, most superclusters are not gravitationally bound as unified objects. The expansion of the universe, currently accelerating due to dark energy, will eventually overcome the gravitational attraction between their components, causing superclusters to disperse over hundreds of billions of years. We live in a special epoch when these magnificent structures exist in their current form, neither too diffuse as in the early universe, nor yet pulled apart by cosmic expansion. This transient quality makes superclusters a kind of cosmic bloom, structures that form, flourish, and eventually disperse across celestial time. They represent a middle phase in the universe's evolution, a period when gravity has had time to create enormous concentrations of matter, but before dark energy's influence fully dominates the largest scales. Even more spectacular than superclusters are the cosmic structures known as walls or sheets. These are enormous flattened concentrations of galaxies that can span hundreds of millions or even billions of light-years across, but remain relatively thin compared to their breadth. They form the largest coherent structures we have identified in the universe, challenging our understanding of how cosmic structure developed. The Great Wall, discovered by astronomers at Harvard in the 1980s, was one of the first such structures identified. Stretching more than 500 million light-years across the northern sky, it appeared as a dense band of galaxies in survey data, standing out dramatically against the relative emptiness on either side. This discovery hinted at cosmic organization on scales larger than previously imagined. Even more extensive is the Sloan Great Wall, identified in data from the Sloan Digital Sky Survey in the early 2000s. At approximately 1.5 billion light-years in length, it represents one of the largest known structures in the universe, containing numerous galaxy clusters and superclusters arranged in a curved filamentary pattern. Its discovery demonstrated that the cosmic web extends coherently across distances so vast that light takes more than 1 billion years to cross them. Perhaps most astonishing is the Hercules Corona Borealis Great Wall, detected through the distribution of gamma-ray bursts, the most energetic explosions in the universe. This structure may span up to 10 billion light-years, or about 1/9 the diameter of the observable universe. While its exact nature remains somewhat uncertain due to the challenges of mapping such distant structures, its apparent size challenges the cosmological principle, which suggests that the universe should appear roughly uniform when viewed at sufficiently large scales. These walls are not solid structures, but rather flattened regions, where the density of galaxies and dark matter significantly exceeds the cosmic average. They form where multiple filaments of the cosmic web align in roughly planar configurations, creating sheet-like concentrations of matter. Voids on either side of these walls enhance their apparent contrast, making them stand out in three-dimensional maps of galaxy distributions. The existence of these enormous structures tells us something profound about the initial conditions of the universe. The seeds for today's walls and superclusters were present in the minute density variations of the early cosmos, variations that originated as quantum fluctuations and were magnified to cosmic scales during the inflationary epoch, immediately after the Big Bang. Gravity's patient work over billions of years has amplified these initially tiny differences into the dramatic structures we observe today. Computer simulations of cosmic evolution reproduce these massive structures when starting from initial conditions consistent with our observations of the cosmic microwave background, the afterglow of the Big Bang. These simulations show how dark matter first forms a web-like network, with ordinary matter later falling into this gravitational scaffolding to form galaxies, clusters, superclusters, and walls. The largest structures emerge naturally from the interplay between gravity, which works to concentrate matter, and cosmic expansion, which works to disperse it. What makes these enormous structures particularly remarkable is that they arise from the same gravitational physics that governs much smaller systems. The same force that causes an apple to fall to Earth also organizes galaxies into filaments and walls spanning billions of light-years. Only the scale and time frame differ. The underlying principles remain the same. From the smallest motion to the largest wall, gravity is the same everywhere. This universality of gravitational physics connects phenomena across an enormous range of scales. The orbits of planets around stars, stars around galactic centers, and galaxies around cluster cores all follow the same fundamental principles described by Einstein's theory of general relativity. Even the largest cosmic structures, despite their immense size, obey these same laws. The mapping of superclusters and walls represents a triumph of observational astronomy. Early galaxy surveys could identify individual galaxies and nearby clusters, but detecting structures spanning hundreds of millions of light-years required surveying huge volumes of space with sufficient detail to reveal the underlying patterns. Projects like the Sloan Digital Sky Survey, the 2-degree Field Galaxy Redshift Survey, and more recently the Dark Energy Survey have progressively revealed larger portions of the cosmic web, allowing astronomers to identify and characterize these enormous structures. These surveys work by measuring not just the positions of galaxies in the sky, but also their redshifts, which indicate their distances from Earth. By combining angular positions with distance information, astronomers create three-dimensional maps of galaxy distributions, revealing the filaments, clusters, superclusters, and walls that make up the cosmic web. The resulting maps show a universe organized into a complex network of interconnected structures, with dense walls and filaments surrounding vast, nearly empty voids. Gravity's influence on these largest structures creates observable effects beyond the distribution of visible galaxies. As galaxies fall toward dense regions like superclusters, they gain velocity in addition to the general cosmic expansion. These peculiar velocities create subtle distortions in our measurements of galaxy distances, distortions that astronomers call redshift space distortions. By carefully analyzing these effects, researchers can map not just where matter is concentrated, but how it is flowing through space. Another gravitational effect visible at these scales is the integrated Sachs-Wolf effect, where photons from the cosmic microwave background gain or lose energy as they pass through the varying gravitational potential of large-scale structures. This creates subtle temperature variations in the microwave background that correlate with the distribution of superclusters and voids, providing an independent confirmation of these structures' gravitational influence. Even more impressive is gravitational lensing on supercluster scales. As light from distant galaxies passes through or near massive structures like superclusters, its path bends slightly, creating systematic distortions in the apparent shapes of background galaxies. By measuring these distortions across large areas of sky, astronomers can map the total mass distribution, including both visible and dark matter, revealing the gravitational backbone of walls and superclusters. These various observational techniques reveal superclusters and walls as key components of the cosmic web, representing the densest and most massive regions within the overall filamentary network. They form where multiple filaments converge or align, creating concentrations of matter that extend across hundreds of millions of light years. Between these dense regions lie the cosmic voids, enormous bubble-like regions of significantly lower than average density. The orientation of these structures does not appear random, but shows alignment across distances larger than expected from standard cosmological models. Some researchers have identified a pattern called the axis of evil, where several large-scale structures appear aligned along a common axis, despite being separated by vast distances. While potentially just a statistical fluke, such alignments could hint at processes operating on scales larger than our current theories easily accommodate. The study of these enormous structures connects to fundamental questions about the nature of the universe. Their size and arrangement provide clues about the initial conditions present after the Big Bang. Their growth rate over cosmic time reflects the influence of dark energy, which counteracts gravity at the largest scales. And their internal motions offer insights into the distribution and behavior of dark matter, which provides most of the gravitational attraction holding these structures together. Moreover, these structures influence galaxy evolution in subtle but important ways. Galaxies in different environments experience different histories, with those in dense regions like superclusters more likely to have undergone mergers and interactions that transform their morphology and star formation activity. The overall distribution of galaxy types, from spiral to elliptical, shows correlations with their position within the cosmic web, reflecting the influence of environment on galactic development. For all their enormous size, superclusters and walls represent just the most prominent features of a continuous cosmic web. The boundaries between one supercluster and another, or between a wall and the surrounding filaments, are not sharply defined but gradual transitions in density. The entire cosmic web forms a single, integrated structure spanning the observable universe, with superclusters and walls simply marking the regions of highest density within this larger network. This continuity reminds us that the universe is fundamentally interconnected. Despite the vast distances separating galaxies, they remain linked through the gravitational web that binds the cosmos together. The motion of our own Milky Way responds not just to nearby masses, but to the accumulated gravitational influence of matter distributed across billions of light years, with more distant contributions diminished but not eliminated by distance. As we drift through this immense cosmic tapestry in our imagination, consider the silence and patience with which gravity has shaped these structures. Unlike the violent processes that form stars or the energetic emissions of active galaxies, the organization of matter into superclusters and walls happens quietly, gradually, as countless masses respond to each other's gravitational pull across billions of years. No individual galaxy knows it is part of a wall or supercluster. Each simply follows the gravitational contours created by all other matter in the universe. This silent collective process has created structures so vast that light itself takes hundreds of millions or even billions of years to cross them. The light we receive from distant parts of a supercluster left those regions when Earth was inhabited by completely different species, or even before our planet had formed. Yet gravity connects all these regions into coherent structures that persist and evolve as unified systems, albeit on timescales far exceeding human experience. The existence of superclusters and walls, also reminds us of our modest place in the cosmic hierarchy. Our Milky Way, home to hundreds of billions of stars and potentially trillions of planets, represents just one galaxy among thousands within our local supercluster. That supercluster, in turn, is just one of countless similar structures scattered throughout the observable universe. This nested hierarchy of structures, extending from planets to walls, spanning billions of light years, places our human concerns in humbling perspective. Yet our ability to perceive and understand these enormous structures represents something remarkable. Through observation, analysis, and theoretical modeling, human minds have comprehended patterns spanning distances so vast that light takes billions of years to cross them. This achievement, mapping the largest structures in existence from our tiny vantage point on Earth, stands as one of science's most impressive accomplishments. As we near the end of this chapter, consider once more the profound continuity of gravitational physics across all scales. The same force that governs the fall of an apple also shapes the largest walls in the cosmos. The same equations that describe a planet's orbit also predict the flow of galaxies towards supercluster cores. The same underlying principle, the curvature of space-time by mass and energy, explains both everyday gravity and the grandest cosmic structures. From the smallest motion to the largest wall, gravity is the same, everywhere. This universality connects phenomena across more than 40 orders of magnitude in size, from subatomic particles to cosmic structures spanning billions of light years. It unifies our understanding of the universe across scales that would otherwise seem incomprehensibly different. In this unity lies a profound truth about the cosmos, that despite its vast diversity of structures and phenomena, it operates according to consistent principles that human minds can comprehend. The superclusters and walls that span billions of light years, for all their unimaginable scale, arise from the same gravitational physics that shapes our daily experience. They remind us that the universe, for all its vastness, is a single, integrated system, bound together by the silent threads of gravity across distances we can barely comprehend. Where light flashes, gravity waits. It is the slow heartbeat of the cosmos. Time flows differently for gravity than for other forces in the universe. While light races across space at 300,000 kilometers per second, and electromagnetic interactions occur essentially instantaneously on human timescales, gravity works with infinite patience. Its effects accumulate gradually over millions and billions of years, slowly but inexorably reshaping the cosmos, according to its simple yet profound principles. This patience makes gravity the great architect of cosmic structure. Where other forces create dramatic, immediate effects, gravity quietly persists, drawing matter toward matter across vast distances and enormous spans of time. The universe we observe today, with its galaxies, clusters, filaments, and walls, represents gravity's patient work since the Big Bang, nearly 14 billion years of gentle but relentless attraction. To truly understand gravity's relationship with time, we must adjust our perspective. Human lives unfold over decades, civilizations over centuries or millennia. But gravity operates on timescales that dwarf even these. The orbit of our Sun around the galactic center takes about 230 million years to complete. The collision between our Milky Way and the neighboring Andromeda galaxy will begin about 4.5 billion years from now. And the largest structures in the universe, the superclusters and walls we explored in the previous chapter, have taken billions of years to form and will continue evolving for trillions more. At these timescales, objects that appear motionless to us are actually in constant, graceful motion under gravity's influence. Galaxy clusters that seem like fixed collections of galaxies are dynamic systems, their member galaxies orbiting the cluster center, while the cluster itself moves through space in response to the gravitational pull of more distant matter. What appears frozen in our astronomical images is merely a single frame in a cosmic dance that unfolds over billions of years. Take our own Milky Way as an example. From Earth, the band of stars that gives our galaxy its name appears unchanging night after night, year after year. Yet every star in that band is in constant motion, orbiting the galactic center at speeds of hundreds of kilometers per second. Our Sun moves through space at about 220 kilometers per second relative to the galactic center, fast enough to circle Earth in just 3 minutes. Despite this rapid motion, the Sun has completed only about 20 galactic orbits since its formation 4.6 billion years ago. So vast is the scale of our galaxy. The stars nearest to us are also in motion, each following its own path through the galaxy. Barnard's star, just 6 light-years away, moves across our sky at the relatively rapid pace of 10.3 arcseconds per year, the fastest apparent motion of any star visible from Earth. Yet even at this rate, it would take about 180 years to move a distance equal to the diameter of the full moon. Stars that appear fixed to the naked eye are gradually redrawing the constellations, but the changes become noticeable only over thousands of years. On larger scales, the motions are even slower relative to the sizes involved. Galaxy clusters orbit within superclusters at speeds of hundreds or thousands of kilometers per second. Yet these speeds translate to barely perceptible changes in their positions over human timescales. So vast are the distances between them. The entire cosmic web evolves as matter flows along filaments toward dense nodes. But this evolution happens so gradually that the overall structure appears static to our observations. This apparent stillness creates an observational challenge for astronomers. We cannot watch cosmic structures evolve in real time, but must infer their dynamics from the snapshot we observe today. This is like trying to understand the flow of a river by looking at a single photograph. Fortunately, the finite speed of light provides a partial solution, allowing us to observe objects at different distances and therefore different periods in cosmic history. By comparing nearby and distant structures, astronomers can trace how galaxies, clusters, and the cosmic web have evolved over billions of years. Computer simulations provide another window into gravity's patient work. Starting from initial conditions consistent with the early universe, these simulations apply the laws of gravity to follow the evolution of cosmic structure over billions of simulated years. The results match our observations remarkably well, confirming our understanding of how gravity gradually transforms a nearly uniform distribution of matter into the complex cosmic web we observe today. These simulations reveal the exquisite sensitivity of gravitational systems to their initial conditions. Tiny differences in the starting distribution of matter amplify over time, eventually leading to significantly different arrangements of galaxies and clusters. This sensitivity, combined with the essentially random nature of the initial density fluctuations, ensures that no two regions of the universe develop identical structures despite following the same physical laws. Yet amid this diversity, patterns emerge. Gravity consistently organizes matter into hierarchical structures, with smaller units combining to form larger ones. It creates filamentary networks rather than uniform distributions or isolated clumps. And it establishes a balance between concentration and dispersal, between the pull of gravity and the push of pressure or orbital motion. These consistent patterns arise from gravity's fundamental nature, its universal attraction weighted by mass and distance. The patience of gravity reveals itself most clearly in the evolution of galaxies. These vast collections of stars, gas, and dark matter do not form fully developed but grow and change over billions of years through a combination of internal processes and external influences, all orchestrated by gravity's gentle pull. Galaxies grow in part by accreting gas from the intergalactic medium, drawing this diffuse material inward to form new stars. They evolve through internal dynamics, as gravitational interactions between stars and gas clouds rearrange their structure over time. And perhaps most dramatically, they transform through mergers with other galaxies. Events that unfold over hundreds of millions of years, as gravity gradually brings the galaxies together in a cosmic collision. These galactic mergers demonstrate gravity's patience particularly clearly. When two galaxies approach each other, their initial interaction creates gravitational disturbances that distort their shapes, drawing out long tidal tails and bridges of stars and gas. As they continue to approach, They may pass by each other before gravity pulls them back for subsequent encounters. Each passage rearranges the galaxies further, dissipating orbital energy and bringing them closer to a complete merger. The entire process, from first approach to final coalescence, typically spans more than 1 billion years, or about 1/15 the age of the universe. During this time, the galaxies gradually lose their original identities and form a new, combined system with properties determined by the masses, gas content, and orbital characteristics of the progenitor galaxies. Spiral galaxies merging in this way often produce elliptical galaxies, their orderly rotation disrupted by the gravitational chaos of the merger. Our own Milky Way bears the scars of such events. Its halo contains streams of stars following similar orbits and sharing similar compositions. The remnants of smaller galaxies torn apart by our galaxy's gravitational field. The Sagittarius stream, a ribbon of stars wrapping around the Milky Way, represents the ongoing disruption of the Sagittarius dwarf spheroidal galaxy, a process that has continued for billions of years and will persist for billions more before the dwarf galaxy is completely absorbed. In about 4.5 billion years, our galaxy will begin a similar but much more dramatic interaction with the neighboring Andromeda galaxy. Currently approaching at about 110 kilometers per second, Andromeda will eventually reach our galaxy, initiating a series of close passages and gravitational distortions that will transform both spiral galaxies into a single elliptical system. Our Sun will likely be thrown into a different orbit during this merger, potentially carrying our solar system far from the center of the newly formed galaxy. What makes these mergers particularly fascinating is that despite their catastrophic implications for the galaxies as systems, they rarely result in collisions between individual stars. The distances between stars are so vast compared to their sizes that even when galaxies intersect, their stars simply pass by each other, like ships in a great ocean. The drama unfolds through gravity's influence rather than direct contact, as the collective gravitational field rearranges the stars' orbits over hundreds of millions of years. Galaxy clusters undergo similar, but even more extensive evolution. Computer simulations show clusters forming hierarchically, with smaller groups falling together to form larger structures. As groups and clusters merge, they create shock waves in the hot intergalactic gas, temporarily heating it to even higher temperatures and causing bursts of X-ray emission. Over time, the combined cluster relaxes into a new equilibrium state, its galaxies following complex orbital paths, shaped by the cluster's overall gravitational field and the influence of its fellow member galaxies. The largest structures, superclusters and walls, evolve more subtly. Unlike galaxies or even clusters, most superclusters are not gravitationally bound as unified objects. The expansion of the universe, currently accelerating due to dark energy, will eventually overcome the gravitational attraction between their components, causing superclusters to disperse over hundreds of billions of years. We live in a special epoch when these magnificent structures exist in their current form, neither too diffuse as in the early universe, nor yet pulled apart by cosmic expansion. This interplay between gravity and expansion defines the largest scales of cosmic evolution. In the early universe, all matter was more closely packed, and gravity's influence relative to expansion was stronger. As the universe expanded, the balance shifted. Regions with higher than average density, where gravity was strongest, separated from the general expansion and began forming the structures we observe today. Regions with lower than average density continued expanding, eventually forming the vast voids between filaments. The accelerating expansion discovered in the late 1990s has profound implications for the future evolution of cosmic structure. As expansion speeds up, driven by the mysterious dark energy that pervades space, gravity's ability to form new structures becomes increasingly limited. Existing gravitationally bound systems like galaxies and clusters will remain intact, but the formation of new superclusters will gradually cease. Eventually, galaxies beyond our local group will recede so rapidly that they become unreachable even in principle, their light too redshifted to detect. In this distant future, gravity's domain will contract to smaller and smaller scales. The local group will consolidate into a single massive galaxy as the Milky Way, Andromeda, and smaller satellites merge over trillions of years. Other isolated galaxies and groups will undergo similar consolidation. But the connections between these island systems will gradually sever as the expansion of space overcomes gravity's ability to bridge the growing distances. Even within these isolated systems, gravity's patient work will continue. Stars will gradually lose energy through gravitational radiation, their orbits slowly decaying. Star formation will cease as gas supplies are exhausted. Stellar remnants, like white dwarfs, neutron stars, and black holes, will increasingly dominate the galaxy. Over unimaginably long timescales, even these remnants will interact gravitationally, some escaping the galaxy, while others fall toward the center or form binary systems. The final fate of matter under gravity's influence depends on the nature of proton decay and other speculative aspects of particle physics. In some scenarios, all ordinary matter eventually disintegrates, leaving only radiation gradually redshifting toward invisibility as the universe continues expanding. In others, black holes become the universe's final gravitational structures, slowly evaporating through Hawking radiation over timescales of 10 to the 100 power years or longer. These cosmic timescales defy human comprehension. Compared to them, our entire species' existence represents less than an eye blink. Yet through science, we can comprehend processes that unfold over billions or even trillions of years, tracing gravity's patient work from the early universe to the distant future. This ability to understand timescales so far beyond our direct experience represents one of humanity's most impressive intellectual achievements. What makes gravity's patience particularly significant is how it contrasts with other physical processes. Nuclear reactions in stars operate millions of times faster than gravitational evolution. Electromagnetic interactions occur essentially instantaneously on cosmic timescales. Even light, which takes years to reach us from nearby stars and millions or billions of years from distant galaxies, moves incomparably faster than the gravitational reorganization of cosmic structure. Yet for all its slowness, gravity ultimately dominates the largest scales and longest timescales. Where other forces create dramatic but localized or temporary effects, gravity quietly accumulates influence across the entire universe and throughout cosmic history. The universe's largest structures, its longest-lived phenomena, all bear gravity's imprint. Consider the oldest stars in our galaxy, some nearly as old as the universe itself, at around 13.5 billion years. These ancient suns have completed dozens of orbits around the galactic center, their paths gradually altered by the collective gravitational influence of countless other stars, gas clouds, and dark matter. Throughout their long lives, the galaxy around them has evolved through gravity's gentle but persistent efforts, changing from a chaotic, gas-rich system actively forming stars to the more ordered, mature spiral we inhabit today. Or consider the cosmic microwave background, the afterglow of the Big Bang that reaches us from all directions. This radiation has traveled for more than 13 billion years, during which time gravity has transformed the nearly uniform universe it left behind into the complex cosmic web we observe today. The subtle temperature variations in this background radiation, just 1 part in 100,000, provided the seeds for all this gravitational evolution, tiny differences in density that gravity gradually amplified into today's vast cosmic structures. What appears chaotic or random in the distribution of galaxies and clusters reveals its deep order when viewed through the lens of gravitational evolution. The positions and velocities of cosmic structures follow patterns predicted by relatively simple gravitational principles applied patiently over billions of years. Even the emptiness of cosmic voids represents gravity's work, as matter has been drawn away from these regions toward denser filaments and clusters. This patient process continues around us even now, imperceptible in human timescales, but relentless over cosmic spans. Our Milky Way is currently absorbing smaller satellite galaxies, their stars gradually integrated into our galactic halo. Andromeda approaches at 110 kilometers per second, covering about 9.5 million kilometers each day, a tiny fraction of the 2.5 million light-years separating our galaxies. Galaxy clusters continue to attract new members and merge with neighboring clusters, their gravitational reach extending across millions of light-years. Gravity's patience teaches us something profound about the nature of enduring influence. In human affairs, we often focus on the immediate, the dramatic, the rapidly changing. But in the cosmos, the most significant forces are often those that work gradually, consistently, over enormous spans of time. Gravity shapes the universe not through sudden interventions but through persistent presence, its influence accumulating slowly but inexorably across the ages. As we drift through the universe in our mind's eye, we witness countless galaxies moving along their gravitational paths, each responding to the combined influence of all other matter. These motions, imperceptible in real time yet cosmic in their implications, represent gravity's ongoing work, its silent rearrangement of the universe, according to its simple yet profound principles. Where light flashes, gravity waits. It is the slow heartbeat of the cosmos, pulsing not in seconds or minutes, but in millions and billions of years. Yet in that patient persistence lies gravity's true power, its ability to shape structures that span millions of light years and endure for billions of years. The universe we observe today represents gravity's patient craftsmanship, its gradual transformation of a nearly uniform early cosmos into the rich, complex, hierarchical structure that surrounds us. And that work continues, unrushed, unceasing, drawing galaxy toward galaxy, star toward star, across distances so vast and timescales so long that we can perceive them only through the accumulated observations and calculations of generations of astronomers. In gravity's patience, we glimpse the true timescale of cosmic evolution, where a billion years passes like a season, and the entire history of humanity occupies less than a moment in the universe's long, gravitational unfolding. Even photons follow the curve of invisible hands. Throughout our journey, we have explored how gravity shapes the distribution of matter across the cosmos, drawing galaxies together into clusters, filaments, and the vast cosmic web. But gravity's influence extends beyond matter to affect even light itself, bending the paths of photons as they travel through curved spacetime. This phenomenon, called gravitational lensing, serves as both a confirmation of Einstein's revolutionary vision of gravity and a powerful tool for exploring the universe's hidden structures. The story of gravitational lensing begins with Einstein's general theory of relativity, published in 1915. Unlike Newton's theory, which treated gravity as a force acting instantaneously across empty space, Einstein described gravity as a curvature of space-time itself. According to this view, mass tells space-time how to curve, and curved space-time tells matter and energy how to move. One of the most profound implications of this theory was that light, despite having no mass, would nevertheless follow the curved paths of space-time. A ray of light passing near a massive object like the Sun would bend slightly toward it, following not the straight line of Euclidean geometry, but the curved geodesic of space-time geometry. Einstein himself calculated that light from a distant star passing near the edge of the Sun would be deflected by about 1.7 arc-seconds, twice the value that would be predicted using Newton's theory and treating light as ordinary particles. This precise prediction provided an opportunity to test general relativity against Newtonian gravity. The opportunity came during a total solar eclipse on May 29, 1919, when a British expedition, led by Sir Arthur Eddington, photographed stars visible near the darkened disk of the Sun. By comparing these positions with photographs of the same stars taken when the Sun was in a different part of the sky, Eddington confirmed that the stars appeared slightly displaced, with the amount of displacement matching Einstein's prediction rather than Newton's. This confirmation of gravitational light deflection made Einstein famous overnight and established general relativity as our most accurate description of gravity. But the full implications of this phenomenon extended far beyond a minor displacement of stellar positions. When a massive object lies directly between an observer and a distant light source, something much more dramatic can occur: a gravitational lens. In 1936, Einstein published a paper describing how a perfectly aligned foreground star could bend light from a background star into a ring-like image, a phenomenon now called an Einstein ring. However, he considered such perfect alignments too rare to be observed, writing, "Of course, there is no hope of observing this phenomenon directly." Einstein underestimated both the scale and the frequency of gravitational lensing. While stars rarely line up precisely enough to create noticeable lensing effects, galaxies and galaxy clusters are both massive enough and large enough to serve as effective gravitational lenses for background objects, creating not just subtle displacements, but dramatic distortions and multiple images. The first gravitational lens was discovered in 1979 when astronomers Dennis Walsh, Robert Carswell, and Ray Wayman observed what appeared to be two identical quasars separated by only 6 arcseconds. These objects, collectively designated QO957 plus 561, became known as the twin quasar. Detailed analysis revealed that these were not separate quasars, but two images of the same distant object. Its light bent around an intervening galaxy to create multiple paths to Earth. Since this landmark discovery, thousands of gravitational lenses have been identified, ranging from multiple images of quasars to stretched arcs of background galaxies and nearly complete Einstein rings. Each demonstrates gravity's influence on light and provides a unique window into the distribution of matter, both visible and dark, across cosmic distances. Gravitational lensing occurs in several regimes, each revealing different aspects of cosmic structure. Strong lensing happens when light passes through the densest regions of massive objects like galaxy clusters, creating dramatically distorted images, multiple copies of the same source, or extended arcs and rings. Weak lensing involves more subtle distortions that can only be detected statistically by analyzing the shapes of many background galaxies. And microlensing occurs when individual stars temporarily brighten a background source as they pass in front of it, an effect used to detect planets around distant stars and to study the galactic distribution of dark objects. What makes gravitational lensing particularly valuable as an astronomical tool is that it depends only on mass, not on whether that mass emits or absorbs light. This makes it one of our most powerful methods for detecting and mapping dark matter, the invisible substance that constitutes about 85% of the universe's total matter, but cannot be observed directly through electromagnetic radiation. When astronomers examine massive galaxy clusters, they often find that the visible galaxies and gas contain nowhere near enough mass to produce the observed lensing effects. The additional gravitational influence must come from dark matter, distributed in halos around individual galaxies and in more extended distributions throughout the cluster. By carefully modeling the lensing effects, researchers can map this invisible component with remarkable precision. One of the most famous examples is the Bullet Cluster, a collision between two galaxy clusters about 3.7 billion light-years away. As the clusters passed through each other, their visible gas collided and slowed down, while their galaxies and dark matter, which do not interact through collisions, continued moving. Gravitational lensing reveals that most of the mass is located where the dark matter should be, not where the visible gas ended up. This spatial separation between visible and invisible mass provides compelling evidence for dark matter as a distinct component that interacts primarily through gravity. Beyond mapping dark matter, gravitational lensing serves as a cosmic telescope, magnifying distant objects that would otherwise be too faint to detect. When light from distant galaxies passes through massive foreground clusters, it can be magnified by factors of 10 or more, allowing astronomers to study galaxies from the universe's earliest epochs. This gravitational magnification has revealed galaxies forming when the universe was less than 500 million years old, objects so distant and intrinsically faint that even our most powerful telescopes could not detect them without nature's assistance. The James Webb Space Telescope, launched in 2021, has leveraged this effect to look deeper into the universe's history than ever before, using massive galaxy clusters as natural gravitational telescopes to study the earliest galaxies and potentially the first stars. This partnership between human technology and cosmic physics extends our observational reach beyond what either could achieve alone. Gravitational lensing also provides a method for measuring cosmic distances and, by extension, the expansion rate of the universe. When a gravitational lens produces multiple images of the same variable source, such as a quasar, The light travel time differs slightly for each image due to both the different path lengths and the gravitational time dilation described by general relativity. By measuring these time delays and modeling the lens geometry, astronomers can determine the absolute distances involved, a technique that contributes to our measurement of the Hubble constant and other cosmological parameters. What makes gravitational lensing particularly fascinating is how it directly visualizes the curvature of space-time that lies at the heart of Einstein's theory. We cannot see space-time itself, but we can observe how light follows its contours, revealing the invisible gravitational landscape shaped by both visible and dark matter. In a very real sense, gravitational lensing allows us to see gravity itself, not directly, but through its effects on light's journey across the cosmos. The mathematics of gravitational lensing follows directly from general relativity. When light passes near a massive object, it follows a curved path determined by the distribution of mass and energy. For a perfect alignment between source, lens, and observer, this creates a symmetric ring. More commonly, slight misalignments produce arcs or multiple images at different positions around the lensing object. The specific pattern of lensed images depends on the exact distribution of mass in the lensing object. A perfectly symmetric mass distribution produces different images than an elongated or irregular one. This sensitivity to mass distribution makes lensing an exceptionally precise probe of cosmic structure, revealing details that would be invisible through other observational techniques. In galaxy clusters, the most massive gravitationally bound objects in the universe, lensing effects can be spectacular. Background galaxies appear stretched into long, thin arcs that partially encircle the cluster core, sometimes extending over hundreds of thousands of light years. In cases of near-perfect alignment, these arcs can form nearly complete rings, their light having traversed multiple paths through the cluster's gravitational field before reaching Earth. These arcs and rings are not just beautiful cosmic accidents, but rich sources of information. Their exact shapes, positions, and magnifications depend on the three-dimensional distribution of matter within the lensing cluster. By carefully analyzing these patterns and comparing them with computer models, astronomers can reconstruct this distribution with remarkable detail, revealing not just the visible galaxies and gas, but the extended halos of dark matter that provide most of the cluster's mass. The precision of these reconstructions continues to improve as observational techniques advance. The Hubble Space Telescope's sharp images have been particularly valuable for gravitational lensing studies, clearly resolving the distorted shapes of background galaxies. The James Webb Space Telescope extends this capability with even greater sensitivity and resolution in infrared wavelengths, while ground-based telescopes with adaptive optics systems provide complementary data at other wavelengths. Beyond individual lenses, astronomers now study weak lensing effects across large areas of the sky. While a single background galaxy may be distorted too subtly to notice, the statistical alignment of many galaxies reveals the gravitational influence of foreground mass concentrations. This technique has evolved from studying individual clusters to mapping the cosmic web itself, tracing the distribution of dark matter across hundreds of millions of light years. Projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory are mapping weak lensing effects across thousands of square degrees of sky, creating the most detailed maps yet of the universe's underlying dark matter scaffolding. These maps reveal how visible galaxies trace, but do not fully sample the underlying mass distribution, with dark matter forming more extended halos and filaments than the visible matter alone would suggest. At even larger scales, gravitational lensing helps constrain cosmological parameters that describe the universe's composition and evolution. The pattern of lensing effects depends not just on the distribution of matter, but on the geometry of space-time itself, which in turn depends on the universe's overall matter density, dark energy content, and curvature. By measuring lensing statistics across cosmic distances, astronomers obtain independent constraints on these fundamental parameters. Gravitational lensing also occurs on much smaller scales within our own galaxy. When a foreground star passes almost directly between Earth and a more distant star, the foreground star's gravity magnifies the background star, causing it to temporarily brighten in an effect called microlensing. Since this alignment depends only on the foreground object's mass, and not on whether it emits light, microlensing can detect objects that would otherwise remain invisible, from brown dwarfs and free-floating planets to stellar remnants like neutron stars and black holes. This technique has proven particularly valuable for exoplanet detection. A planet orbiting a foreground star creates a brief additional spike in brightness if it happens to align with the background star during a microlensing event. Unlike other exoplanet detection methods, microlensing can find planets at almost any distance from their host stars, including those in very wide orbits similar to our own outer planets. This capability complements other techniques that are more sensitive to planets in close orbits, providing a more complete census of planetary systems. Monitoring millions of stars for these brief brightening events requires automated surveys that continuously observe densely populated fields like the galactic bulge. Projects like the Optical Gravitational Lensing Experiment have discovered thousands of microlensing events, contributing significantly to our understanding of stellar populations and planetary systems throughout the galaxy. The concept of using gravity as a lens extends beyond visible light to all forms of electromagnetic radiation, and even to gravitational waves themselves. Radio astronomers have identified numerous gravitationally lensed quasars, with the radio emission from distant active galactic nuclei bent into multiple images by intervening galaxies. These radio lenses often provide cleaner data than optical observations, as radio waves penetrate dust that might obscure optical images. In the future, gravitational wave detectors may observe lensed signals from merging black holes or neutron stars, with the gravitational radiation bent by intervening mass concentrations just as electromagnetic waves are. Such observations would provide unique tests of general relativity, confirming that gravitational waves and light follow the same curved paths through spacetime, despite their fundamentally different nature. Even more exotic possibilities exist. Theoretical work suggests that in some cases, gravitational lensing could create not just multiple images, but infinitely many images arranged in complex patterns. Under certain conditions, light could orbit a black hole multiple times before escaping toward an observer, creating a series of increasingly squashed images that approach a limiting curve called the photon ring. The Event Horizon Telescope, which produced the first direct image of a black hole in 2019, may eventually resolve these subtle effects, providing new tests of strong field gravity. The relationship between gravity and light reveals a profound unity in physical law. Though gravity and electromagnetism appear as distinct forces in our everyday experience, Einstein's general relativity shows that both are aspects of the same underlying reality: the geometry of spacetime. Light follows the curvature of spacetime not because of any force acting upon it, but because that curvature defines the shortest path between points. In this sense, light's curved trajectory near massive objects is not a deflection from its natural path, but a revelation of what that path truly is in curved spacetime. This unity extends to our understanding of cosmic structure. The same gravity that binds galaxies into clusters also bends the light by which we observe them, creating a seamless connection between the dynamics of cosmic objects and the paths of the photons that carry information about them to our telescopes. The light we receive has been shaped by the very structures it allows us to study, a recursive relationship between observer and observed mediated by gravity's influence. Gravitational lensing reminds us that our view of the cosmos is not direct, but filtered through the gravitational landscape it traverses. The universe we see is subtly, but significantly different from the universe that exists, its image distorted by the mass distributions along each line of sight. In a very real sense, we observe not the universe itself, but its gravitational echo, the pattern of light that reaches us after negotiating the curved paths of spacetime. Yet far from being a limitation, this gravitational filtering provides additional information about the cosmos. The distortions themselves reveal aspects of cosmic structure that would otherwise remain invisible, particularly the distribution of dark matter across space. What might initially seem like a complication becomes a powerful tool for exploring the universe's hidden components. As our ability to detect and analyze gravitational lensing continues to advance, we develop an increasingly detailed map of the universe's gravitational landscape. Each lensed image, each distorted galaxy, each microlensing event adds another data point to this map, gradually revealing the invisible architecture that shapes the visible cosmos. Through gravitational lensing, we trace not just where matter is, but how it is distributed. Not just what we can see, but what remains hidden from direct view. In a profound sense, gravitational lensing completes Einstein's revolution in our understanding of gravity. Where Newton saw an invisible force acting across empty space, Einstein revealed a curvature of space-time itself. Gravitational lensing makes this curvature observable, translating the abstract mathematics of general relativity into visible patterns of light that we can capture with our telescopes. Through these patterns, we witness not just the effects of gravity, but the very nature of space and time, as Einstein understood them. Even photons follow the curve of invisible hands. This simple statement encapsulates both the phenomenon of gravitational lensing and its deeper significance for our understanding of the cosmos. The invisible hands are not forces in the Newtonian sense, but the curved geometry of space-time itself, shaped by the distribution of mass and energy throughout the universe. And in following these curves, light reveals both the visible and invisible structure of a universe shaped by gravity's subtle influence across cosmic distances and cosmic time. Emptiness is not the absence of gravity, it is gravity's gentle outline. Throughout our journey, we have focused primarily on where matter is concentrated: galaxies, clusters, filaments, and the vast cosmic web. But between these structures lie enormous regions of significantly lower density, cosmic voids that span tens or even hundreds of millions of light years. These apparent emptinesses, far from being irrelevant to our story, represent another essential manifestation of gravity's influence on cosmic structure. Voids are not truly empty. They contain a sparse population of galaxies, typically less than 1/10 the cosmic average density, along with extremely diffuse gas and dark matter. What defines them is not absolute emptiness, but relative emptiness, a significant underdensity compared to the universe as a whole. They appear as vast bubbles between the filaments of the cosmic web, occupying most of the universe's volume while containing only a small fraction of its matter. The existence of these voids emerges naturally from the same gravitational processes that create denser structures. In the early universe, slight variations in density were present, with some regions containing slightly more matter than average, and others slightly less. As gravity amplified these initial differences, pulling matter toward overdense regions, it simultaneously drew matter away from underdense regions. The result was a cosmic topography of peaks and valleys, with matter flowing from the valleys toward the peaks, leaving the valleys progressively emptier. This process accelerated as structure formed. Gravity created a positive feedback loop in which regions that started with slightly less matter than average became increasingly depleted as that matter was drawn towards surrounding denser regions. What began as minor underdensities evolved into the vast voids we observe today, their boundaries defined by the filaments and walls that surround them. Computer simulations of cosmic evolution reproduce these voids with remarkable fidelity, confirming our understanding of how gravity shapes not just where matter accumulates, but also where it does not. These simulations show voids forming hierarchically, with smaller underdense regions merging to create larger ones in a process that mirrors, in reverse, the hierarchical assembly of clusters and filaments. The largest voids identified in galaxy surveys span enormous distances. The Bootes void, discovered in 1981, extends across approximately 330 million light-years, yet contains only about 60 known galaxies, making it one of the emptiest regions in the nearby universe. The local void, closer to our Milky Way, spans about 150 million light-years and influences the motion of galaxies in our cosmic neighborhood, including our own. What makes these voids particularly fascinating is that they are not static features, but dynamic participants in cosmic evolution. They grow over time as more matter flows out of them towards surrounding filaments. They interact with each other, merging to form larger voids when the filament separating them thins and breaks, and they influence the motions of galaxies both within and around them through their gravitational effects. This dynamic nature challenges our intuition about gravity, which we typically associate with attraction toward mass rather than movement away from emptiness. Yet both reflect the same underlying physics. In general relativity, gravity manifests as the curvature of spacetime caused by the distribution of mass and energy. This curvature affects not just regions where matter is concentrated, but the entire fabric of spacetime, including regions where matter is sparse. Voids represent regions where spacetime is less curved than average, creating a relative gravitational repulsion compared to denser surroundings. Galaxies near the boundaries of voids experience what astronomers call the void phenomenon, a net gravitational force pushing them away from the void and towards surrounding filaments. This is not a new force, but simply the natural consequence of the uneven distribution of matter, which creates a gravitational gradient from less dense to more dense regions. The motion of galaxies in and around voids provides valuable information about cosmic parameters. The expansion rate of voids differs slightly from the average expansion rate of the universe, an effect that depends on the overall cosmic density, the nature of dark energy, and the behavior of gravity at large scales. By measuring how voids evolve over time, astronomers can constrain these fundamental aspects of cosmology, complementing other methods like galaxy clustering and the cosmic microwave background. Voids also serve as unique laboratories for studying galaxy formation and evolution. The small population of galaxies within voids, sometimes called void galaxies, develops under conditions dramatically different from those in denser environments. With fewer nearby galaxies, void galaxies experience fewer gravitational interactions and mergers. They encounter less intergalactic gas as they move through space, reducing the effects of ram pressure stripping that can remove gas from galaxies in clusters. These environmental differences affect void galaxies' properties. Studies show that they tend to be smaller, bluer, and more gas-rich than their counterparts in denser regions, with more active star formation relative to their mass. They also tend to be behind in their evolutionary development, resembling galaxies from earlier cosmic epochs, when most galaxies were still gas-rich and actively forming stars. The existence of galaxies in voids presents a mild puzzle for structure formation theories. If voids represent regions from which matter has flowed away, how did enough matter accumulate locally to form galaxies within them? The answer appears to lie in the small-scale density fluctuations present even within generally underdense regions. Just as the universe as a whole contained slight variations in density, voids themselves are not perfectly uniform, but contain smaller-scale peaks and valleys. Galaxies form at the small-scale peaks within the larger-scale valley of the void. This hierarchical pattern of density variations, with smaller fluctuations superimposed on larger ones, characterizes the entire universe and explains the distribution of structure at all scales. Voids contain subvoids, just as filaments contain subfilaments and clusters contain subclusters. This nested structure, emerging naturally from the random initial density field and gravity's subsequent influence, creates the rich, multiscale tapestry of cosmic structure we observe. The boundaries between voids and surrounding structures represent particularly interesting regions. As matter flows out of voids, it accumulates at their edges, creating relatively dense ridges and walls. These boundaries often contain galaxies in transition, their properties intermediate between those of void galaxies and those in denser filaments. The void boundaries also fluctuate over time as more matter leaves the void, causing them to expand into the surrounding medium. When multiple voids expand adjacent to each other, the matter between them compresses into increasingly dense and narrow filaments. Eventually, these filaments may break, allowing neighboring voids to merge into larger structures. This process of void merging, the reverse of the more familiar process of structure merging, plays a significant role in the evolution of the cosmic web, gradually simplifying its topology as smaller voids combine into larger ones. The void's role in cosmic evolution extends beyond their immediate neighborhoods to influence the largest scales of structure. By evacuating matter from vast regions, voids contribute to the formation and enhancement of distant structures, sending material flowing along filaments toward cluster intersections. In this way, they participate in a cosmic recycling program, their lost matter becoming part of the most massive structures in the universe. This relationship reminds us that emptiness and fullness, voids and clusters, represent complementary aspects of the same gravitational process. Neither exists without the other. Both emerge from gravity's influence on the initially almost uniform matter distribution. The cosmic web is defined as much by where matter is not as by where it is, with voids outlining the filaments, just as filaments outline the voids. The study of cosmic voids has advanced tremendously in recent decades, as larger galaxy surveys have mapped the universe in 3 dimensions with increasing detail. Projects like the Sloan Digital Sky Survey have identified thousands of voids, allowing statistical analysis of their properties and evolution. Newer surveys with even greater depth and coverage continue to refine our understanding of void populations across cosmic time. Complementing these observations, sophisticated computer simulations follow the formation and evolution of voids, from the early universe to the present, enabling direct comparison between theoretical predictions and observed void properties. These simulations show voids emerging naturally from realistic initial conditions, their sizes, shapes, and emptiness, matching what we observe in galaxy surveys. What makes voids particularly valuable for cosmological studies is their sensitivity to dark energy, the mysterious component driving the accelerated expansion of the universe. Because voids are relatively empty, dark energy's effects manifest more strongly within them than in denser regions where matter's gravitational attraction partly counteracts cosmic acceleration. By tracking how voids evolve over cosmic time, astronomers can probe dark energy's properties with unique sensitivity. In the long silence ahead, gravity will be the last voice. Throughout our journey, we have explored gravity's role in shaping cosmic structure. From individual galaxies to the vast cosmic web, we have witnessed its patient work across billions of years, drawing matter together against the background of an expanding universe. But this relationship between gravity and expansion raises a profound question. What is the ultimate fate of our universe? Will gravity eventually halt the cosmic expansion, pulling all matter back together? Or will expansion continue forever, gradually overcoming gravity's reach at the largest scales? For much of the 20th century, cosmologists framed this question as a competition between 2 opposing influences: the inward pull of gravity and the outward momentum of expansion, inherited from the Big Bang. The balance between these influences would determine whether the universe was closed, eventually recollapsing in a big crunch, open, expanding forever at a gradually decreasing rate, or flat, expanding forever, with the expansion rate approaching 0 at infinite time. This framework suggested that the fate of the universe depended primarily on its average density. If the density exceeded a critical value, gravity would eventually win, halting and reversing the expansion. If the density fell below this critical value, expansion would continue forever, with gravity gradually losing influence over the largest scales. And if the density exactly matched the critical value, expansion would continue but asymptotically slow to 0, a delicate balance between gravity and expansion. Measuring this cosmic density became a central goal of observational cosmology. Galaxy surveys mapped the distribution of visible matter, while theoretical considerations suggested the presence of substantially more dark matter. Additional constraints came from the cosmic microwave background, the afterglow of the Big Bang, whose detailed pattern of temperature fluctuations depends on the universe's overall composition and geometry. By the 1990s, these measurements increasingly suggested a universe very close to the critical density, implying a flat geometry that would expand forever, but at an ever-decreasing rate. This finding aligned with theoretical expectations from cosmic inflation, a period of exponential expansion in the universe's first moments that naturally drives the cosmos toward flatness. But a profound discovery awaited. In 1998, 2 independent teams of astronomers published results from studying distant supernovae, violent stellar explosions so bright they can be seen across billions of light years. These supernovae appeared fainter than expected, indicating they were farther away than their redshifts would suggest in a universe where expansion was slowing due to gravity. The only explanation was that the expansion of the universe was not slowing but accelerating, with distant galaxies receding at ever-increasing speeds. This unexpected acceleration required a new component in our cosmic inventory: a mysterious energy pervading empty space and pushing galaxies apart. Physicists named it dark energy, acknowledging both its invisible nature and its unknown composition. Unlike matter, which becomes more dilute as the universe expands, dark energy appears to maintain a constant density over time, causing its influence to increase relative to gravity as the universe grows larger. The discovery of cosmic acceleration fundamentally changed our understanding of the universe's fate. No longer a simple competition between gravity and initial expansion momentum, the cosmic future now depends on the nature of dark energy and how its density might evolve over time. Current observations indicate that dark energy constitutes about 68% of the universe's total energy content, with dark matter contributing 27% and ordinary visible matter just 5%. With dark energy dominant and apparently constant, the most likely future involves ever-accelerating expansion, a scenario cosmologists call the Big Freeze or heat death. In this future, galaxies beyond our local group will recede at ever-increasing speeds, eventually becoming so redshifted that they fade from view entirely. The observable universe will gradually empty as more objects cross a cosmic horizon beyond which light cannot reach us, leaving our local region increasingly isolated in an effectively empty cosmos. This isolation will occur not because distant galaxies move beyond some boundary, but because space itself expands between us and them, carrying them away faster than their light can travel toward us. Eventually, even light emitted now from galaxies outside our local group will never reach us, as the intervening space expands too quickly for the light to make headway against it, like a swimmer trying to reach shore against an insurmountable current. Within our local group, gravity will maintain its dominance over dark energy's expansive influence. Our Milky Way and the neighboring Andromeda galaxy remain on a collision course, scheduled to begin merging in about 4.5 billion years. Over longer timescales, the entire local group will likely consolidate into a single massive galaxy as its members gradually spiral together under their mutual gravitational attraction. This pattern will repeat throughout the universe, with gravitationally bound systems remaining intact while the spaces between these systems grow ever larger. Galaxy clusters will hold together internally while separating from other clusters at accelerating rates. The cosmic web will gradually simplify as connections between distant structures stretch beyond the cosmic horizon, leaving isolated island universes surrounded by effectively empty space. Within these island universes, gravity will continue its patient work over timescales, far exceeding the current age of the universe. Stars will gradually exhaust their nuclear fuel, ending their lives as white dwarfs, neutron stars, or black holes depending on their initial mass. Gas supplies will dwindle, choking off new star formation. Galaxies will grow increasingly populated by stellar remnants rather than active stars, their appearance shifting from the bright spirals and ellipticals we observe today to darker, more compact configurations. Over even longer timescales, measured in trillions of years, gravitational interactions between these stellar remnants will eject some from their host galaxies, while causing others to spiral toward the center. Central supermassive black holes will grow by consuming stars and gas that venture too close, gradually incorporating a larger fraction of each galaxy's total mass. If protons decay, as some theories predict, ordinary matter will eventually disintegrate, leaving only radiation and black holes. The black holes themselves will ultimately evaporate through Hawking radiation, a quantum process that causes them to lose mass over unimaginably long timescales. The most massive black holes would take about 10 to the 100 power years to evaporate completely, a time so vast that it dwarfs the current age of the universe by a factor of 10 billion. After the last black hole evaporates, the universe would contain only increasingly red-shifted radiation and potentially stable elementary particles, separated by ever-growing distances as cosmic expansion continues. The temperature would approach absolute zero, and organized structures would cease to exist. Gravity, having shaped the universe from its earliest moments, would find less and less matter to influence as particles separate beyond any possibility of interaction. This scenario of ever-accelerating expansion leading to a cold, empty universe represents our best current understanding of cosmic fate based on the observed properties of dark energy. However, this understanding remains provisional, as the true nature of dark energy continues to elude us. Several theoretical possibilities could alter this projected future, leading to dramatically different outcomes. If dark energy's density changes over time, rather than remaining constant, the universe's fate would depend on how this density evolves. Some models predict that dark energy might eventually weaken or disappear, allowing gravity to reassert its influence at the largest scales. In this scenario, cosmic acceleration would eventually cease, returning us to a universe where expansion continues but gradually slows, more aligned with the open universe cosmologists envisioned before the discovery of acceleration. More exotic possibilities exist. If dark energy's density increases over time, cosmic acceleration would not just continue but intensify, potentially becoming so extreme that it tears apart gravitationally bound systems like galaxies and eventually atoms themselves. This scenario, called the Big Rip, would end the universe in a violent disintegration rather than a gradual cooling. Current observations place tight constraints on such models, making a Big Rip unlikely but not definitively ruled out. Alternatively, if what we interpret as dark energy actually represents a modification of gravity at large scales, rather than a new energy component, different futures become possible. Various modified gravity theories have been proposed to explain cosmic acceleration without invoking dark energy, each with different implications for the universe's long-term evolution. Even more speculative scenarios involve quantum effects that might eventually create a new universe within our own, either through random quantum fluctuations or through intentional actions by advanced civilizations. While such possibilities lie at the frontier of theoretical physics and cannot be evaluated with current observations, they remind us that our understanding of cosmic evolution, at the longest timescales and most extreme conditions, remains inherently uncertain. What all these scenarios share is the central role of gravity in determining cosmic fate. Whether as the force that might eventually halt expansion, as the local influence that maintains structure against a background of acceleration, or as the fundamental interaction whose nature we might not yet fully understand, gravity remains the key player in the universe's long-term evolution. This relationship between gravity and cosmic fate has deep philosophical implications. The universe we inhabit exists in a delicate balance, with gravity strong enough to form complex structures like galaxies, stars, and planets, but not so strong as to cause a rapid recollapse. This balance, whether coincidental or necessary, has allowed sufficient time for stars to burn, planets to form, and life to evolve, at least on our small world, orbiting an ordinary star. Had gravity been significantly stronger relative to the universe's initial expansion, the cosmos might have recollapsed before stars could complete their life cycles, preventing the formation of the heavy elements essential for planets and life. Had gravity been much weaker, matter might never have gathered into galaxies and stars, leaving a cold, diffuse universe incapable of developing complex chemistry. Our existence thus depends on gravity falling within a range that allows for the formation of stable structures over timescales measured in billions of years. Whether this represents a cosmic coincidence, an inevitable outcome of physical law, or one possibility among many in a vast multiverse, remains an open question at the intersection of physics, cosmology, and philosophy. The eventual fate of the universe also raises profound questions about meaning and purpose in a cosmos with a finite or infinite future. If the universe faces a heat death of ever-increasing isolation and dispersal, does this diminish the significance of the structures and forms that temporarily arise within it? Or does it heighten the preciousness of order and complexity emerging against the background of increasing entropy? Different philosophical and religious traditions have grappled with these questions in various ways. Some find meaning in the temporary nature of all things, appreciating the beauty of forms that arise and pass away. Others seek transcendence beyond physical existence, envisioning consciousness or spirit surviving the material universe's fate. Still others focus on the present moment and the wonder of existing at all, regardless of what the distant future might hold. Science itself does not answer these philosophical questions, but provides the context within which we ask them. By revealing the likely fate of our physical universe, cosmology frames our reflection on what meaning we might find within it, while leaving the nature and source of that meaning to other domains of human inquiry. What science does tell us with increasing precision is the timescale over which different cosmic processes will unfold. Stars like our Sun typically burn for billions to trillions of years, depending on their mass. Galaxies remain recognizable for trillions of years before stellar evolution and gravitational interactions fundamentally alter their appearance. Proton decay, if it occurs, would manifest over timescales of at least 10 to the 33 power years. Black hole evaporation extends to 10 to the 100 power years and beyond. These timescales, increasing exponentially as we look further into the future, create an almost infinite canvas for cosmic evolution. Even with accelerating expansion, gradually isolating different regions, the universe will remain a place of ongoing gravitational processes, the timescales that dwarf the current age of the cosmos by factors beyond human comprehension. This immensity of cosmic time reminds us of our brief moment in the universe's long history. Humanity has existed for less than 1 million years, civilization for only a few thousand, and modern science for mere centuries. Set against the universe's future, measured in trillions or quadrillions of years, our entire species' existence represents less than an eye blink in cosmic evolution. Yet through science, we can comprehend processes that unfold over these vast timescales, projecting the consequences of physical laws into a future we will never witness. This ability to understand time periods far beyond our direct experience represents one of humanity's most remarkable intellectual achievements, allowing us to place our brief moment in the context of cosmic past and future. The relationship between gravity and expansion also reminds us of the dynamic tension that characterizes our universe. Neither a static collection of fixed objects nor a formless dispersion of particles, the cosmos maintains a balance between concentration and dispersal, between the pull of gravity and the push of expansion. This balance creates the rich structure we observe, from galaxies to the cosmic web, while allowing for ongoing evolution as these influences continue their interplay across cosmic time. The discovery of dark energy and cosmic acceleration transformed our understanding of this balance, revealing that what we once saw as a simple tug of war between gravity and initial expansion momentum actually involves a third player, the mysterious energy pervading empty space itself. This discovery, one of the most significant in modern cosmology, reminds us that our understanding of fundamental physics remains incomplete, with profound implications for the universe's ultimate fate. Observational programs continue to refine our measurements of dark energy's properties and cosmic acceleration's precise rate. Projects like the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and the upcoming Vera-C Rubin Observatory track how the universe's expansion has changed over time by measuring the distances and redshifts of billions of galaxies. Space missions like Euclid and the Nancy Grace Roman Space Telescope will extend these measurements with even greater precision, constraining dark energy models and potentially revealing whether its influence changes over cosmic time. If dark energy's density does change, even slightly, the implications for the universe's fate could be profound. A strengthening dark energy could lead to a Big Rip scenario, while a weakening one might allow gravity to eventually reassert its dominance at the largest scales. Current measurements favor a constant dark energy density, consistent with Einstein's cosmological constant, but improved observations may reveal subtle variations that would significantly alter our projection of cosmic future. Meanwhile, theoretical physicists continue exploring possible explanations for dark energy's nature, from quantum field effects in vacuum energy to modifications of Einstein's theory of gravity at the largest scales. These investigations connect the universe's future evolution to its fundamental structure, seeking a deeper understanding of both through unified theories that would explain why dark energy exists and how it relates to gravity and other forces. What makes the question of cosmic fate particularly fascinating is how it connects the largest scales and longest timescales to the fundamental physics that governs subatomic particles. The same theories that describe the behavior of elementary particles in particle accelerators also inform our understanding of the universe's beginning in the Big Bang and its eventual fate, billions or trillions of years future. This unity of physical law across such vastly different contexts represents one of science's most profound achievements. Even our home is drifting. Even we are being pulled by the invisible. Throughout our journey, we have traveled from the familiar to the incomprehensible, from the gravity we feel to the gravity that shapes the universe's largest structures. Now we return to our cosmic home, the Milky Way galaxy, to understand its place in the gravitational tapestry of the universe. Far from being an isolated island in space, our galaxy exists in constant gravitational relationship with everything around it, its past and future determined by these invisible connections. The Milky Way, a barred spiral galaxy containing approximately 200 billion stars, orbits within a small collection of galaxies called the Local Group. This gravitationally bound family includes our nearest large neighbor, the Andromeda Galaxy, along with the Triangulum Galaxy, and several dozen smaller dwarf galaxies. The entire group spans about 10 million light-years and contains a few trillion solar masses of material, most of it in the form of dark matter. Within this local group, gravity orchestrates a complex ballet of motion. The Milky Way and Andromeda, the two largest members, orbit around their common center of mass, gradually approaching each other due to their mutual gravitational attraction. Smaller galaxies like the Large and Small Magellanic Clouds orbit the Milky Way as satellites, while others orbit Andromeda or follow more complex paths influenced by both major galaxies. These relationships are not static, but evolve over time. Tidal forces gradually disrupt the smaller satellite galaxies, drawing streams of stars away from them and toward their larger hosts. Some satellites will eventually be completely absorbed, their stars becoming indistinguishable parts of the larger galaxy's halo. Others may survive for many billions of years, their orbits gradually decaying as gravitational interactions drain their orbital energy. Our Milky Way has participated in this process of gravitational cannibalism throughout its history. Its halo contains the remnants of numerous smaller galaxies, accreted over billions of years, their stars now orbiting as part of our galaxy, but often distinguishable by their shared motions and chemical compositions. The Sagittarius Dwarf spheroidal galaxy, discovered in 1994, is currently being torn apart by our galaxy's tidal forces, its stars forming a long stream that wraps around the Milky Way multiple times. This ongoing accretion represents gravity's patient work of galactic assembly. Rather than forming all at once, large galaxies like the Milky Way grow through the gradual accumulation of smaller systems drawn in by gravitational attraction. This hierarchical growth continues today and will culminate, billions of years from now, in the merger between the Milky Way and Andromeda, forming a massive elliptical galaxy that some astronomers whimsically call Milkomeda. But the local group does not exist in isolation. It forms part of a much larger structure called the local sheet, a relatively flat arrangement of galaxy groups spanning tens of millions of light-years. This sheet, in turn, connects to the Virgo supercluster or local supercluster, a vast collection of galaxy groups and clusters centered around the Virgo cluster about 54 million light-years away. Recent analysis has revealed that even this supercluster represents just one region of an even larger structure called Laniakea, meaning immense heaven in Hawaiian. This enormous gravitational collection contains about 100,000 galaxies spread across a region roughly 500 million light-years in diameter. What defines Laniakea is not just the physical proximity of its galaxies, but their shared motion. Galaxies within Laniakea are flowing together through space, drawn by gravity toward dense regions like the Great Attractor. These nested layers of structure, from the Milky Way to the local group, to the local sheet to Laniakea, illustrate how gravity organizes matter across multiple scales simultaneously. Each layer influences the others, with larger structures providing the gravitational context within which smaller ones evolve. Our galaxy's motion through space reflects the combined gravitational pull of all these structures, from the nearby Andromeda Galaxy to the distant concentrations of mass at Laniakea's core. The Milky Way moves through space at approximately 630 kilometers per second, relative to the cosmic microwave background, the reference frame that represents the universe's overall expansion. This motion combines several components: the rotation of Earth around the Sun, the Sun's orbit around the galactic center, the Milky Way's motion within the local group, the local groups flow toward the Virgo cluster, and the larger-scale streaming of matter toward the Great Attractor and other massive concentrations within Laniakea. This cosmic motion carries us through space at breathtaking speed, yet it remains imperceptible in our daily experience due to its smooth, consistent nature and the vast distances involved. In the time it takes to read this sentence, the Earth has traveled hundreds of kilometers through space as part of this great gravitational journey. Over a human lifetime, we move trillions of kilometers through the cosmos, carried by our planet, our star, and our galaxy as they respond to the gravitational pull of distant matter concentrations. Our location within this cosmic structure influences conditions on Earth in subtle but important ways. The Milky Way's position in a relatively quiet region between major spiral arms, about 27,000 light-years from the galactic center, provides a relatively stable environment with moderate radiation levels and a low frequency of nearby supernova explosions. Had our solar system formed closer to the galactic center or within a dense spiral arm, more frequent stellar explosions and higher radiation levels might have made Earth less hospitable to complex life. Similarly, the Milky Way's location within the local group and larger cosmic structures affects the night sky we observe. The concentration of satellite galaxies around the Milky Way reflects our position within the local group's gravitational landscape. The distribution of distant galaxy clusters across our sky reflects our location within Laniakea and our perspective on neighboring superclusters like Perseus Pisces and the Shapley concentration. This connection between our local conditions and the universe's largest structures reminds us that Earth exists as part of an interconnected cosmic whole, its environment shaped by gravitational relationships spanning hundreds of millions of light-years. The stability that allows life to flourish on our planet depends partly on our particular location within this vast gravitational tapestry. The Milky Way's gravitational interactions also shape its internal structure and evolution. The spiral arms that wind through our galaxy's disk are not fixed material structures but density waves, patterns of compression that move through the galactic disk like ripples on a pond. Stars and gas move through these patterns, temporarily bunching together as they pass through an arm before spreading out again. The gravitational influence of the spiral pattern affects star formation, gas dynamics, and the orbits of individual stars, including our Sun. Similarly, the Milky Way's central bar, a straight concentration of stars spanning thousands of light-years across the galactic center, represents a gravitational pattern that influences material throughout the inner galaxy. This bar rotates as a unit, completing one revolution about every 250 million years. Its gravitational field creates resonances in the disk, concentrating material at specific radii and helping to maintain the spiral pattern. At the very center of this complex gravitational system lies Sagittarius A star, the supermassive black hole at the Milky Way's core. Containing the mass of about 4.3 million suns compressed into a region smaller than our solar system, this gravitational behemoth influences the orbits of stars within the central few light-years, while playing a relatively minor role in the galaxy's overall gravitational field. The stars closest to this central black hole move at tremendous speeds, with the star S2 reaching velocities of thousands of kilometers per second during its closest approach. Beyond the visible disk, the Milky Way's gravitational reach extends into a vast halo of dark matter, containing 5 to 10 times more mass than the visible galaxy and spanning hundreds of thousands of light-years in all directions. This dark halo provides most of the gravitational binding that holds the galaxy together, allowing stars in the outer disk to orbit at speeds that would tear the galaxy apart if only visible matter were present. The Milky Way's past and future are written in its gravitational relationships. Evidence suggests our galaxy formed from the merger of many smaller systems, their stars now mixed throughout the galactic disk and halo. Some of these ancestral systems can still be identified as coherent streams or clumps of stars sharing similar orbits and chemical compositions, ghostly remnants of once independent galaxies now incorporated into our own. Our galaxy's future will be similarly shaped by gravitational encounters. The approaching collision with Andromeda, scheduled to begin about 4.5 billion years from now, will dramatically transform both galaxies. Computer simulations suggest their first approach will trigger gravitational distortions, pulling out long tidal tails of stars and gas. They will swing past each other, then loop back around for subsequent encounters, each passage bringing them closer to a complete merger. After several billion years of this gravitational ballet, the two spiral galaxies will merge into a single, larger, elliptical galaxy. The ordered spiral patterns will dissolve as stars are thrown into more random orbits. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other and merge, releasing enormous gravitational energy in the process. Our Sun will likely be thrown into a different orbit during this merger, perhaps ending up far from the center of the new galaxy. If humanity or its descendants still exist, they will witness a dramatically altered night sky, with the familiar band of the Milky Way replaced by a more three-dimensional distribution of stars stretching in all directions. This future merger illustrates gravity's ongoing role in shaping cosmic structure. The same force that formed galaxies in the early universe continues to draw them together, gradually building larger structures through countless such collisions. Our Milky Way, like all galaxies, represents not a final form, but a temporary configuration in a continually evolving gravitational landscape. The study of our galaxy's place in the cosmic tapestry has advanced tremendously in recent years, thanks to missions like the European Space Agency's Gaia spacecraft. Launched in 2013, Gaia is creating the most detailed three-dimensional map ever of the Milky Way, measuring the positions and motions of approximately 1 billion stars with unprecedented precision. This vast dataset reveals the galaxy's structure and dynamics in extraordinary detail, including the subtle effects of past gravitational interactions and ongoing accretion events. Complementing Gaia's optical observations, radio telescopes map the distribution and motion of gas throughout the galaxy, revealing how material flows along spiral arms and around the galactic center. X-ray observatories detect the hot gas in the galactic halo, tracing the effects of supernova explosions and the interaction between our galaxy and the intergalactic medium. Gamma-ray telescopes map the most energetic processes, including the annihilation of dark matter particles in dense regions. Together, these observations create a comprehensive picture of the Milky Way as a dynamic, evolving system, its structure and motion determined by both internal processes and external gravitational influences. Far from being a static collection of stars, our galaxy emerges as a living entity, constantly changing as it responds to gravitational forces both near and far. This dynamic nature extends to our own solar system. The Sun orbits the galactic center at about 220 kilometers per second, completing one circuit approximately every 230 million years. This orbit is not perfectly circular, but slightly elliptical, causing the Sun to move slightly closer to and then farther from the galactic center over millions of years. Our orbit also includes small up and down oscillations through the galactic plane, with a period of about 60 million years. These orbital variations may influence conditions on Earth over geological timescales. Some researchers have suggested connections between the Sun's passage through denser regions of the galaxy and periods of increased comet impacts on Earth, potentially linking extinction events to our galaxy's gravitational influence. While such connections remain speculative, they highlight how our planet's history may be influenced by its journey through the gravitational landscape of the Milky Way. Even our Sun's formation, roughly 4.6 billion years ago, depended on galactic gravitational processes. The gas cloud that collapsed to form our solar system likely received the gravitational nudge that initiated its collapse from a nearby supernova explosion, itself part of a wave of star formation triggered by the compression of interstellar gas as it passed through a spiral arm. In this sense, the very existence of our solar system and our planet reflects the Milky Way's gravitational dynamics. The elements that form Earth and our bodies also connect us to galactic gravitational processes. The carbon, oxygen, iron, and other heavy elements essential for life were forged in previous generations of stars and then dispersed through supernova explosions, themselves gravitational events where a star's core collapses under its own weight. These enriched materials later incorporated into the cloud that formed our Sun and its planets, making us, in a very literal sense, children of the galaxy's gravitational history. This connection reminds us that we exist not separate from the cosmic tapestry, but as an integral part of it. The atoms in our bodies have experienced the gravity of stellar interiors, the explosive release of supernovae, the gentle collapse of interstellar clouds, and the steady pull of our sun. They now participate in Earth's gravity and in the countless small gravitational interactions that make up our daily experience. Even the rhythm of our lives connects to cosmic gravity. The tides that shape our oceans result from the moon's and sun's gravitational pull. The seasons that structure our year arise from Earth's orbital motion around the sun. The very force that keeps our feet on the ground extends, in increasingly subtle form, across the entire universe, connecting us to the most distant galaxies through the invisible threads of gravitational influence. As we near the end of this chapter, consider once more our Milky Way's place in the universe's gravitational tapestry. Neither the center of creation nor an isolated island in space, our galaxy exists as one node in a vast network of gravitational relationships, its past shaped by countless mergers and interactions, its future determined by its ongoing approach toward Andromeda and the larger flow of matter toward distant concentrations of mass. Within this cosmic context, Earth orbits an ordinary star in an ordinary galaxy, distinguished not by any central position, but by the remarkable fact that it has produced beings capable of comprehending the gravitational tapestry in which they exist. Through science, we have gradually mapped our place in this vast structure, from our position in the solar system, to our location in the Milky Way, to our galaxy's place in the local group, Laniakea, and the cosmic web. This understanding represents not just an intellectual achievement, but a profound shift in our relationship with the cosmos. Where ancient peoples imagined Earth at the center of creation, we now see ourselves as travelers through a universe shaped by gravity's patient work across billions of years. Our planet, our sun, our galaxy, all move in response to the combined gravitational influence of distant matter, their paths determined by the universe's underlying structure. Even our home is drifting. Even we are being pulled by the invisible. This simple statement captures a profound truth about our place in the cosmos. We exist not as stationary observers, but as participants in the universe's gravitational dance, carried through space at hundreds of kilometers per second by forces we cannot see but have learned to understand. In that understanding lies one of humanity's greatest achievements, the recognition of our true place in the cosmic order, not at its center, but as one small part of its vast, interconnected whole. Gravity may be deeper than we know, a thread not between galaxies, but between realities. Throughout our journey, we have explored gravity as the force that shapes cosmic structure, from the orbits of planets to the vast filaments of the cosmic web. We have witnessed its patient work across billions of years, drawing matter together against the background of an expanding universe. Yet for all we have learned about gravity's effects, its fundamental nature remains one of physics' greatest mysteries. As we conclude our exploration, let us venture into more speculative territory, considering what might lie beyond our current understanding of gravity, or perhaps deeper within it. Einstein's general relativity, our most accurate description of gravity, reveals it not as a force in the conventional sense, but as a curvature of space-time itself. This revolutionary insight transformed our understanding of gravity's nature, but raised new questions about how it relates to the universe's other fundamental forces and to the quantum realm that governs subatomic particles. Unlike electromagnetism and the strong and weak nuclear forces, gravity has resisted integration into the quantum framework that successfully describes the universe's other fundamental interactions. This incompatibility between general relativity and quantum mechanics becomes critical in extreme conditions, such as the interiors of black holes, or the first moments after the Big Bang, where both gravitational and quantum effects play essential roles. Theoretical physicists have pursued various approaches to resolve this contradiction and develop a quantum theory of gravity. String theory proposes that fundamental particles are not point-like but tiny, vibrating strings whose different vibration patterns create the particles and forces we observe. In this framework, gravity emerges naturally alongside the other forces, potentially unifying physics at the most fundamental level. Loop quantum gravity takes a different approach, suggesting that space-time itself has a discrete, granular structure at the smallest scales, like fabric woven from quantum threads. This granularity would only become apparent at the Planck scale, about 10 to the negative 35th meters, far smaller than anything we can currently detect. At these scales, space-time would no longer appear smooth and continuous, but quantized into minimal units, fundamentally changing how gravity operates. Other approaches include causal set theory, which models space-time as a collection of discrete events connected by causal relationships, and asymptotic safety, which proposes that gravity naturally becomes better behaved at high energies, rather than breaking down as current theories predict. Each approach offers a different vision of gravity's true nature, with distinct implications for our understanding of the universe's most extreme environments. These theoretical explorations extend beyond mathematical curiosity to questions about the universe's deepest structure. Some versions of string theory, for instance, require extra spatial dimensions beyond the three we experience. These additional dimensions might be compactified into incredibly tiny loops, explaining why we don't perceive them in daily life, while allowing them to influence physics at fundamental scales. The existence of such extra dimensions could have profound implications for gravity's behavior. Gravity might leak into these dimensions, explaining why it appears so much weaker than the other fundamental forces. This weakness represents one of physics' great puzzles: why the gravitational attraction between two protons is about 10 to the 36th times weaker than their electrical repulsion, a discrepancy known as the hierarchy problem. Even more speculative is the possibility that gravity connects not just objects within our universe, but different universes within a larger multiverse. Various theories suggest that our universe might be one bubble in a vast foam of universes, each with its own physical laws and constants. Some propose that black holes might create new universes through their singularities, regions where space-time curves so extremely that our current theories break down. In this scenario, pioneered by physicist Lee Smolin, each black hole's singularity might give birth to a new universe with slightly different physical properties than its parent. This process would create a kind of cosmic evolution, with universes that produce many black holes generating more offspring universes than those that don't. Over time, this selection pressure would favor universes with physical laws conducive to black hole formation, potentially explaining why our universe's parameters seem finely tuned for complexity and structure. Wormholes represent another speculative connection between different regions of space-time or even different universes. Einstein's equations permit these tunnel-like shortcuts through space-time, though keeping them open would require exotic forms of matter with negative energy density, something not conclusively observed in nature. If stable wormholes could exist, they would create gravitational bridges between distant regions, fundamentally altering our understanding of cosmic connectivity. The study of black holes continues to reveal surprising connections between gravity and quantum mechanics. Stephen Hawking's discovery that black holes emit radiation and eventually evaporate creates an information paradox that challenges our understanding of both gravitational and quantum laws. Information that falls into a black hole appears lost when the black hole evaporates, violating a fundamental principle of quantum mechanics that information cannot be destroyed. Proposed resolutions to this paradox include the possibility that information escapes through subtle quantum correlations in the Hawking radiation, that it remains encoded on the black hole's event horizon, or that it enters a different universe altogether. Each solution requires rethinking aspects of either general relativity or quantum mechanics, pointing toward a deeper theory that would reconcile these seemingly contradictory frameworks. Recent theoretical work suggests that space-time itself might emerge from more fundamental quantum entanglement between particles. This perspective, developed by researchers like Juan Maldacena and Leonard Susskind, proposes that gravitational connections between different regions of space-time correspond to quantum entanglement between particles in those regions. The motto ER equals EPR captures this correspondence, linking Einstein-Rosen bridges, wormholes, with the Einstein-Podolsky-Rosen paradox that highlighted quantum entanglement's strange properties. This connection between gravity and quantum entanglement hints at a profound unity underlying apparently distinct physical phenomena. If gravity fundamentally represents the entanglement structure of the universe's quantum information, then what we experience as the force holding planets in orbit and shaping cosmic structure might actually be a macroscopic manifestation of microscopic quantum relationships. Observational evidence for these speculative ideas remains limited. Detecting quantum aspects of gravity would require either astronomical observations of extreme environments like black hole horizons and the early universe, or particle physics experiments at energies far beyond current capabilities. The Laser Interferometer Gravitational Wave Observatory, LIGO, and similar detectors have opened a new window on the universe by directly detecting gravitational waves, but observing quantum gravity effects would require far greater sensitivity. Similarly, particle accelerators like the Large Hadron Collider probe physics at high energies, but remain many orders of magnitude away from the Planck energy, where quantum gravity effects would become directly observable. Future technologies might narrow this gap, but complete experimental verification of quantum gravity theories may remain beyond reach for generations. Despite these observational challenges, theoretical exploration continues to yield insights that change how we understand gravity and its relationship to the cosmos. The holographic principle suggests that all the information contained in a volume of space can be represented on its boundary, reducing the three-dimensional physics within a region to two-dimensional physics on its surface. This principle, inspired by black hole thermodynamics, implies that gravity in the bulk of spacetime emerges from quantum field theory on the boundary, a relationship formalized in the ante-de Sitter conformal field theory correspondence. Such connections between gravity and information theory suggest that what we experience as the pull between masses might reflect something even more fundamental: the way information is structured and processed at the universe's deepest level. In this view, gravity becomes not just one force among many, but a manifestation of how reality itself is organized and interconnected. As we conclude our journey through gravity's domain, we find ourselves not at an endpoint, but at the threshold of deeper questions. The same force that keeps our feet on the ground and shapes the cosmic web might connect to the quantum fabric of reality, to extra dimensions beyond our perception, or even to other universes in a vast multiverse. Gravity may indeed be deeper than we know, a thread not just between galaxies, but potentially between realities. This possibility reminds us that our understanding of the universe remains a work in progress, with each answer revealing new questions at more fundamental levels. The gravity we have explored throughout our journey, from its everyday effects to its cosmic implications, may represent just the visible surface of a deeper reality whose full nature continues to elude us. Between every star and every world, there is space, but between every galaxy, there is connection, a pull, soft and sure. Gravity is not just the weight of things, it is the thread of everything. Sleep now and drift across it. The universe will hold you. Our journey through gravity's realm has taken us from the fall of an apple to the collision of galaxies, from the orbit of planets to the vast filaments of the cosmic web. We have witnessed gravity's patient work across billions of years, drawing matter together into ever more complex arrangements against the background of an expanding universe. As our exploration concludes, let us reflect on what gravity reveals about the nature of our cosmos and our place within it. Gravity stands apart from other forces in the universe. While electromagnetic forces can both attract and repel, while the strong and weak nuclear forces operate only at subatomic distances, gravity acts as a universal attractor, reaching across the entire cosmos with infinite range. It shapes everything from the smallest asteroid to the largest supercluster, creating order from what would otherwise be chaos. Yet for all its strength in shaping cosmic structure, gravity is paradoxically the weakest of the fundamental forces. The electrical repulsion between two protons is about 10 to the 36 power times stronger than their gravitational attraction. Gravity dominates the universe only because it always attracts, never repels, allowing its influence to accumulate across vast collections of matter, and because the other forces typically balance themselves through positive and negative charges or colors. This curious balance, with gravity strong enough to form stars and galaxies but weak enough to allow stable orbits and complex structures, creates the conditions that make our existence possible. Had gravity been significantly stronger or weaker, the universe might not have developed the rich complexity we observe, the delicate balance between concentration and dispersal that allows for solar systems, planets, and life itself. Throughout our journey, we have encountered gravity not as an external force imposed on the universe, but as an intrinsic aspect of spacetime itself. Einstein's revolutionary insight revealed that what we experience as gravitational attraction actually represents the curvature of space and time in the presence of mass and energy. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This deep connection between gravity and the fabric of reality itself suggests that in studying gravity, we study not just one force among many, but the fundamental architecture of the cosmos. The paths of planets around stars, of stars around galactic centers, and of galaxies through the cosmic web, all follow the contours of spacetime, revealing its hidden geometry through their motion. We have also witnessed gravity's patience, its ability to work gradually over timescales that dwarf human experience. While light flashes across the cosmos in an instant, gravity accumulates its influence over billions of years, slowly but inexorably reshaping the universe according to its simple yet profound principles. The cosmic structures we observe today represent gravity's patient work since the Big Bang, nearly 14 billion years of gentle but relentless attraction. This patience reminds us of our place in cosmic time. Human civilization has existed for a mere moment in the universe's long history, yet through science, we comprehend processes that unfold over billions of years. We track the gradual merger of galaxies, the formation of clusters and superclusters, the weaving of the cosmic web through gravity's subtle influence across vast distances and enormous spans of time. Gravity also reveals what we cannot see. The motions of visible matter, from stars orbiting galactic centers to galaxies moving within clusters, indicate far more mass than we can detect through light. This invisible component, which we call dark matter, reveals itself only through its gravitational effects, yet constitutes about 85% of all matter in the universe. Like a cosmic sculptor working with invisible clay, gravity makes manifest the shape of what remains hidden from direct view. Similarly, the bending of light around massive objects, an effect predicted by Einstein and now routinely observed by astronomers, allows us to map both visible and invisible matter across cosmic distances. Gravitational lensing transforms the distortions in distant galaxies' images into detailed maps of the intervening mass distribution, revealing the dark matter halos and filaments that provide the universe's underlying structure. Throughout our exploration, we have encountered gravity as a connective force, binding the universe into a single, integrated system. Despite the vast emptiness of space, nothing truly exists in isolation. Each object, from a tiny moon to a massive galaxy cluster, responds to the gravitational influence of everything else, creating a cosmic web of relationship that spans the observable universe. This connectivity extends to our own experience. The atoms in our bodies were forged in stellar interiors and scattered through space by supernovae, themselves gravitational events where stars collapse under their own weight. These atoms gathered into our solar system through gravity's gentle pull, accumulating into the Earth and eventually into the complex forms of life that include ourselves. In a very real sense, we exist because of gravity's patient work across cosmic time. Even now, gravity connects us to the cosmos in ways both obvious and subtle. The weight we feel against Earth reflects our place in the gravitational field of our planet, which itself orbits the Sun in response to its gravitational pull. Our solar system moves around the galactic center, completing one orbit approximately every 230 million years. And our Milky Way galaxy drifts through space, drawn by the combined gravitational influence of Andromeda, the Virgo cluster, and more distant mass concentrations. This constant motion carries us through the cosmos at breathtaking speed, yet it remains imperceptible in our daily experience due to its smooth, consistent nature. In the time you have spent listening to this journey through gravity's domain, Earth has traveled thousands of kilometers through space as part of this great gravitational dance. We are not stationary observers, but travelers on a planet that itself journeys through the cosmos, guided by the invisible threads of gravitational influence. As we conclude, consider once more the silence of gravity's work. Unlike light, which announces itself to our eyes, or sound, which speaks to our ears, gravity operates without sensory fanfare. We feel its effects as weight, as the stable orientation that distinguishes up from down, but its deeper operations across cosmic distances and timescales transcend direct perception. Gravity speaks not through brightness or noise, but through relationship, through the subtle curvature of space-time that guides every object's path through the universe. In this silence lies gravity's profound message, that beneath the universe's apparent chaos and diversity exists an underlying unity, a shared response to the same fundamental principle. The same physics that causes an apple to fall governs the collision of galaxies. The same relationship between mass and space-time curvature shapes both planetary orbits and the vast filaments of the cosmic web. Gravity reveals the universe not as a collection of separate objects, but as a single, integrated system, bound together by invisible connections that transcend distance and time. Between every star and every world, there is space, but between every galaxy, there is connection, a pull, soft and sure. These words capture the essence of our cosmic reality, the tension between separation and relationship that characterizes the universe at all scales. The vast distances between cosmic objects exist alongside the gravitational relationships that bind them together, creating not isolation but interconnection across the cosmos. Gravity is not just the weight of things, it is the thread of everything. More than a force that pulls objects downward, gravity represents the fundamental connectivity of the universe, the invisible architecture that shapes everything from the smallest particle to the largest supercluster. In gravity, we encounter not just a physical force, but a principle of cosmic relationship, a thread that weaves throughout existence, binding the universe into a coherent whole. Sleep now and drift across it. The universe will hold you. As we conclude our journey, let these words carry you into rest, secure in the knowledge that the same gravity that holds planets in orbit and binds galaxies into clusters also holds you safely against Earth. The universe we have explored is not alien territory, but your cosmic home, its laws and patterns part of the reality in which you exist. As you drift towards sleep, imagine yourself floating among the stars, free from Earth's familiar pull, yet still connected to the cosmic whole through gravity's gentle embrace. Picture the vast structures we have explored, from spiral galaxies to the filaments of the cosmic web, all shaped by the same fundamental principle that keeps you connected to Earth. Feel yourself as part of this grand gravitational tapestry, a conscious participant in the universe's ongoing evolution. The universe will hold you, now and always, cradled in the invisible arms of gravity's embrace. Sleep and drift, and know that you belong to the cosmos, bound to it by the most fundamental relationship in nature, the silent thread that connects everything to everything else across the vastness of space and time.